Hello and welcome to the second workshop on neural fields beyond conventional cameras. The first one ran in ICCV of last year, and now we're doing it again, this time with me as host. And basically, I'll keep this very brief since we are already behind schedule. But to bring some motivation to why you're here, why this is interesting, and why we might want to continue work in this area, in sort of the last years, we have seen a lot of flavors of imaging, computational imaging, computational photography, uh, basically non-RGB imaging, everything from telescopes to microscopes to MRIs, raw imaging, reflection removal, et cetera, et cetera, et cetera. And what do all these things have in common? What they have in common is the fact that all of them make a huge amount of data, and they all usually make this data with some complex physical phenomena, whether that be, photon collection or some Fourier domain stuff where you're just sampling electromagnetic radiation directly, or anything in between. And I think a lot of people in this room and beyond have sort of gone to compact continuous representations like neural fields or sort of stochastically optimized models like Gaussian splatting and said, hey, that's a really neat way to embed a bunch of data and a bunch of physical priors into one model. Wouldn't it be cool if we did Gaussian splatting, but for infrared? Or wouldn't it be cool if we embedded all this like cryo-EM knowledge we have about protein conformations directly into our reconstruction model to get something out of our system? And so the schedule for today is basically right now, welcome to the introduction. We're going to have a couple of keynotes on how exactly you can do this and some excellent demonstrations of this work. Then after the keynotes, which will be about an hour and a half, we will have 3 paper spotlights chosen from the submitted works to this workshop and more excellent demonstrations of how can this be done in the wild. Following that, we will walk 1 quadrillion miles to Exhibition Hall D to have our poster session and a small coffee break and to stretch our legs. And then after 4 p.m., we'll come back here for 3 more excellent keynotes. And last but not least, we will have a panel discussion where basically there were some submitted questions. We might take some live questions, and we'll chat about what burning questions people have in the field and what information we can bestow upon them. Great. With that, all I'd like to do is just thank everyone who has helped make this workshop possible. So that includes the reviewers, the organizers, and you for showing up and listening to this. And with no further ado, I will switch to our first speaker. And we will swap in our laptop. All right.
Hello, everybody. Welcome. Please hang on for 1 minute. Should be muted. Okay. All right. Hello, everyone. I'm Katie Skinner. I'm an assistant professor in the robotics department at the University of Michigan, and I'm excited to talk to you about our work on splatting beyond the visible spectrum, so Gaussian splatting for radar, sonar, and more. So I work in field robotics. Field robotics is a really exciting field where we deploy robots on land, sea, and space and underwater applications. Let's see if my videos will work. There we go. So we get to do a lot of fun things. I spent last week on a boat up in Lake Huron deploying robots in Thunder Bay National Marine Sanctuary to survey shipwreck sites up there. We work on perception challenges for marine robotics, including scene understanding and 3D reconstruction, as well as localization. Underwater environments are really challenging, which makes them also really interesting. We have really interesting operational challenges just deploying robots in the field. We don't have access to Wi-Fi, GPS, things that we're used to having on land. So we really have to rely on our onboard sensors for carrying out a lot of the tasks that we care about. There's challenges for data collection, which means we have in relative to other applications, a lack of available data for things like training large machine learning models that we're used to on land. And we also have some pretty unique perception challenges that I'll talk about in a bit. On the other hand, we also work on autonomous driving applications. Of course, autonomous driving has seen a lot of advances in recent years in vision due to the acceleration of data collection and data labeling. But there's still some pretty interesting perception challenges there too, right? When we think about deploying cameras at all times of day, all types of weather conditions, we can see a lot of effects that we maybe aren't quite well equipped to handle yet. So these are the types of challenges that we think about in my lab. And one solution that we have for them is to really turn away from RGB cameras, right? Maybe in some cases, RGB cameras are not the best modality to work in. So that has moved us towards thinking about how to apply perception algorithms to sonar and radar, which is what I'll focus on today. So let's dive into marine robotics first. And I like to give a little overview of kind of what we're working on in this space. So this is a map of Thunder Bay National Marine Sanctuary. This is a sanctuary that's jointly run by NOAA and the state of Michigan. Let me just hide these meeting controls. There we go. It's a really unique area because of all the shipping channels in the past. There have been a lot of shipwrecks in this area. So all of those black dots, if you can see them, are known shipwreck sites. There's 100 known shipwreck sites and 100 suspected sites. So this makes it a really interesting region for us to think about large-scale data collection of shipwrecks. So we've been working up there for several years now, deploying robots in Lake Huron to collect all sorts of data, but side scan data, as well as imaging data. So this is an imaging survey that we did at the Monahans shipwreck site several years ago with our ROV platform. And we take all of this imagery and we use this to build 3D models that are really useful to the marine archaeologists that study these sites, right? They can use these models to maybe, compare year after year the changes that are going on in the lakes. So I think this is a really interesting application, but there's some caveats here, right? So this model looks great after 2 years of data collection. This is the best looking model that I have, right? So I have cherry picked this result to show in my presentations. This model was computed offline, so it took several days with a lot of computing resources, a lot of data to construct this model. And you can see there's distorted color because of the underwater effects that we haven't corrected for. In general, while this model is pretty complete, a lot of our other models are prone to holes and sparsity because of missing data or because of degradation of images when we have really poor visibility. So these are all challenges that we have with RGB images underwater, right? So the survey that I just showed you is actually a pretty clear survey site, but in this survey site, it's a bit hazier. So until something gets really up close to you, you can't quite make out what it is. So as I mentioned, this motivates us to think about using different sorts of sensors underwater. And acoustics is a modality that we use very regularly. So this is an imaging sonar example, not of a shipwreck site, but an imaging sonar example to show kind of what the other data sources that we have access to are. So today I'm going to talk about our work using Gaussian splatting for imaging sonar. So with imaging sonar, we still want to be able to complete the same sorts of tasks that we do with camera imagery. We want to be able to deploy our robots, take some captured sonar images, think about tasks like scene understanding, like object detection if we're trying to detect this rock, or semantic segmentation. And as I mentioned, also 3D reconstruction for some of these downstream tasks, right? So we still want to be able to perform all of the same perceptual tasks that we think about for camera systems as well when we think about deploying robots with sonar systems. But there's a lot of challenges to working with sonar data. One is just the lack of publicly available data sets for carrying out some of these tasks that we care about, right? So we have maybe the object detection or segmentation task. We have a couple of publicly available data sets, not from my group, but from the community for carrying out machine learning tasks on segmentation and detection. You can see the number of images available even for these publicly available data sets is quite small compared to what we have access to from autonomous driving applications. And 3D reconstruction, I would say, has gained interest for sonar, the sonar community, but it is still quite an open challenge, especially to get dense 3D reconstruction that we can use for downstream tasks. So there are some gaps in existing real data sets. This has caused the community to turn to simulation. So this is a simulation environment that we've developed called Ocean Sim, but you can see we're still quite a far way off from generating simulated sonar data that's realistic. Part of this challenge is just the challenge of modeling noise characteristics, modeling the really unique characteristics of acoustic data. So this has led us to maybe why you're all here too, is recent work in NERFs and Gaussian splatting. So NERFs, as you know, are have really great potential. They've been really powerful for things like novel view synthesis, data synthesis, 3D reconstruction, especially dense 3D reconstruction, and even denoising and multimodal fusion. So this has been really exciting for us to see and has given us some inspiration for maybe what we could use for our toolbox. Of course, NERFs are on the more expensive side to train and render, so this has led the field to Gaussian splatting, which can render images much faster than NERFs. So we have work in both of these areas, but today I'm going to focus on our work in Gaussian splatting for sonar data and other sensors. So we recently released Sonar Splat, which performs novel view synthesis of imaging sonar for Gaussian splatting. This paper is currently under review, but it is available on arXiv if you are interested. So Sonar Splat takes in a robot trajectory. This is our robot in a water tank on campus, as well as sonar image inputs, and it enables novel view synthesis, image destreaking, which I'll talk about in a bit, as well as 3D reconstruction of underwater scenes. So just to give some background on the imaging sonar formation model, the geometry is shown on your right. So you can see it gives a return in spherical coordinates. So you have range from the sensor, azimuth angle, spanning out from either side. All returns from a given range and azimuth interval are summed into the same bin, which means that we have this elevation angle ambiguity in sonar data, which is pretty unique to work with. And we also have view-dependent images as well. So because of shadowing effects, the images can actually look quite different from one view to the next. We also have some interesting noise characteristics. So in particular, we're going to focus on azimuth streaking, which you can see on the bottom. So these are, again, the left is a water tank image, the right is an image from a river where we deployed a known target. And you can see where these arrows are pointing, what's known as azimuth streaking. So azimuth streaking occurs when there's strong returns. The returns from incident angles close to parallel at a specific range bin. And it causes a streak along the azimuth direction. And this can be quite challenging to handle in perception algorithms, right? We don't really have a lot to work with here from the literature in terms of how to think about developing machine learning methods or 3D reconstruction methods that are robust to these very unique types of noise. So these are some of the challenges that we are looking at. There has been some, of course, recent interest in applying radiance fields like neural rendering and Gaussian splatting to imaging sonar. So there are a couple of works in neural rendering or NERFs looking at sonar. There is previous work in space carving for 3D reconstruction of sonar in general, and some recent works on RGB sonar fusion. So there is one prior work that we were motivated by called Z-Splat that performs Gaussian splatting for RGB and sonar, but they mainly focused on RGB rendering and reconstruction, and they really use sonar more for initialization or for guidance for training. So our method sonar splat performs Gaussian splatting for sonar only, and we also model really unique noise characteristics of sonar that enable us to then go back and perform denoising of sonar, but also generate really realistic sonar images in novel view synthesis, as well as higher quality 3D reconstruction models. So I'm going to talk a little bit about our contributions for sonar splat. So here's an overview of the whole pipeline. Hopefully you can see it in the back, but it takes as input a posed sonar image, and we have an initialization step to initialize Gaussians along the elevation arc of the sonar to give an opportunity for it to resolve the elevation ambiguity. We developed a range and azimuth splatting model for the imaging sonar image formation model. And then we also have a separate modeling component where we're modeling azimuth streaking specifically, because this was one noise characteristic that added a lot of challenges for working with the data that we have from our specific sonar. We're performing loss on the ground truth sonar image to output a rendered sonar image. So I'll go into a little bit more of the splatting model. So this, when we go back to the papers that first looked at applying neural rendering, volumetric rendering with imaging sonar, just to give kind of a overview of that process. You can see it's quite similar to the RGB image volumetric rendering pipeline. Just a couple of differences here. We have the sum across elevation angles and azimuth angles and range to handle the spherical coordinates. And we also have the intensity of emitted sound and range gain in front. But we're still looking at a transmittance, which is the probability of reaching a point in the scene without collision along some range direction, and the density at that point as well. So converting this to sonar splat, range, and azimuth splatting, this is our splatting model for our unsaturated image. So not accounting for azimuth streaking, we handle that as a separate process. But you can see, again, it's pretty similar to the imaging model, except that now we have an acoustic reflectance, opacity, transmittance. So this gives us our unsaturated image that does not contain azimuth streaking. And then if we turn to our azimuth streaking model, the goal here is to come up with a probabilistic way to model azimuth streaking in a differentiable manner so that we can train our azimuth streaking model. So see if I can run all this. So if you see a zoomed in version of de-streaked image on the left, what we've done is we have a per Gaussian probability of azimuth streaking. The reason it's per Gaussian is because that allows us to perform multi-view consistent azimuth streaking. And what we do is that if we have no Gaussian in a range bin that has a high probability of azimuth streaking, we apply a gain of 1. But in other cases where there is a higher probability of azimuth streaking, we have an adaptive gain strategy to handle or model azimuth streaking. So if there's a Gaussian with high probability of azimuth streaking in one range bin, we adaptively suppress the other Gaussians in that range bin. So you can see this is kind of leading to two azimuth streaks on the right here. Our adaptive gain module can also handle the case where there's a couple of areas or a couple of probabilities that have high probability of azimuth streaks as well. So just going back to, so this gives us our pipeline, our two main components of our pipeline. And third, we have an elevation sampling densification strategy, which isn't shown here, but just as I mentioned, allows us to initialize Gaussians along an elevation arc to resolve the elevation ambiguity. Okay, so showing a few of our results. We collected our own data set for evaluation because there's limited access to data sets that have the ground truth that we care about for quantitative evaluation. So Here's a few examples from our data set. We have both a river site and a water tank site that we collected data in, and we deploy targets that we have ground truth for. So we have a rock target, for example, that we put in the water tank, and we have a 3D model of it that we collected in air. We also have a 3D model of our tank because we were able to collect a scan of it while it was empty. So we have ground truth that we can use for quantitative evaluation in this case. And our data collection platform is a modified blue ROV platform. So this is a robot we buy off the shelf, and then we outfit it with different sensors and design different sensor suites depending on the application. So the first task I'll show is our 3D reconstruction results. So you can see the robot taking some inspection trajectory and the ground truth on the bottom. We compared to the space carving algorithm, which had trouble resolving this infrastructure pillar in our water tank. And with Sonar Splat, we can get a slightly improved reconstruction. So this is promising, we think, for enabling dense 3D reconstruction from imaging sonar for underwater scenes, for things like infrastructure inspection, or even thinking about mapping shipwreck sites in the Great Lakes. We also looked at novel view synthesis. So in the top scene, we're taking a forward trajectory, but with Sonar Splat, we can perform novel view synthesis and slightly alter the view from that trajectory that we use for training. In the bottom, similarly, we do kind of an orbit around this pillar, and we can modify the viewing angles of that orbit and perform novel view synthesis using Sonar Splat for that scenario as well. So you can see we get very realistic, high fidelity sonar image synthesis because we're modeling some of these unique characteristic noise types that side scan or imaging sonar contains. So here's just a couple more examples of our novel view synthesis. Go back. So you can see comparing to Z-Splat, although I'll mention we ran Z-Splat only with sonar, not with RGB. And as I mentioned, it was really designed for RGB rendering. And we also compared to NuSys NGP, which is one of the volumetric rendering methods for sonar. And you can see that Sonar Splat provides a really high quality novel view renders. Just to show some zoomed in views, so you can see the noise that we're able to model as well. You can see that it looks quite realistic from the real data. And we have quantitative results in the paper too. So if you're interested, I encourage you to look for the paper on arXiv. I'll mention, since this is a Gaussian splatting method, we also have improved rendering speed compared to the NERF models, although we didn't optimize for rendering speed. Z-Splat has much faster rendering still, so that is an area for future work for us. So one interesting thing about our method, because we are explicitly modeling azimuth streaking, that allows us to think about things like de-streaking. So you can see the captured image and our novel view synthesis in the middle. We can go in and remove the azimuth streaks from our novel view synthesis to provide a de-streaked image, which is a pretty unique capability of this method because we're modeling the noise specifically. So there is a problem space called image de-streaking. So we leverage some metrics from image de-streaking community in order to perform quantitative evaluation of this task as well. So in summary, Sonar Splat allows us to perform high fidelity sonar image synthesis and de-streaking. We can model the azimuth streaking and perform image restoration. And our future goal is now to move towards RGB sonar fusion for the tasks of 3D reconstruction in real underwater environments. So this was our dive into underwater, but I want to briefly talk about our work in autonomous vehicle applications as well. So, of course, there's a lot of interest in data synthesis on land too. There's been a lot of excitement around using NeRFs and Gaussian splatting for novel view synthesis, but also for generating data for training machine learning models, both for RGB images and for LiDAR. We have been pretty interested in radar for a while now, as many of you may be as well, because of the use cases for radar in some of these more challenging vision domains, such as in poor weather, foggy conditions, rain and snow. And we also like to note that a lot of platforms that are being deployed in the real world have radar enabled already. So we can really leverage the sensors that we have access to on these vehicles that are being deployed if we can develop methods for using radar for things like scene understanding and and 3D reconstruction. So we've been working on Gaussian splatting for radar to enable data synthesis and 3D reconstruction in these highway scenes. We note there's been prior work called radar fields that we were inspired by that perform 3D reconstruction and novel view synthesis with a NeRF-based framework for automotive radar. And we found that radar fields, while it performs very nice reconstruction, does not necessarily model radar noise characteristics that are unique to radar sensors. So we turned to we were inspired to kind of start to incorporate the knowledge of radar noise sources into Gaussian splatting framework. So a couple of the noise sources we considered were the multipath effect, which is due to both reflectance off of multiple sources before it reaches the sensor. We also have cases of receiver saturation with a very high return in one angle, as well as speckle noise, which is like background noise in the image. So these are the noise types that we were interested in modeling. And I won't go into as much detail for the radar splat system, but just to give an overview that we're able to take in 2D radar inputs and use our radar splat model to perform 3D reconstruction, as well as novel view rendering and radar inverse rendering as well. For the sake of time, I'll give a brief overview, but just to say that we do have a poster in this workshop later on during the break. My student Frank will be presenting, so please find Frank, he's right there as well, so that we can, if you're interested in learning more about radar splat. So for the sake of time, I won't go into too much detail of the technical approach, but just to tease some results, radar splat performs very accurate noise modeling, which allows us to generate high fidelity radar view synthesis as well. We also experimented with 3D reconstruction. And again, because we're able to separate the noise multipath sources from the real objects in the scene, we're able to improve the 3D reconstruction results, especially in the cases of really noisy radar data, such as with a lot of multipath effects. And then because we're modeling these noise sources explicitly, we can also think about things like radar inverse rendering. We're separating out the target or the return from the real target, multipath noise, and background noise as well. So again, I know that was a brief overview, but encourage you to check out our workshop poster and go talk to Frank and ask him a lot of questions about his work. So hopefully you will take this opportunity. So in the last couple of minutes, I just want to mention a couple of other projects we've been thinking about in case you're interested in talking about them as well. So we've also been interested in thermal data, especially for robotics and autonomous vehicle applications. We have work focused on NeRFs, especially for deblurring and modeling blur in thermal images under fast motion. Because we're focused on robotics applications, we've also been moving towards real-time implementation of NeRFs and Gaussian splatting frameworks in kind of end use cases. So we have some work in NeRFs for LiDAR integrated in real-time SLAM systems to perform dense mapping and state estimation. And then lastly, I think a big benefit of a lot of these methods is the ability to perform multimodal fusion. So we have thought about camera LiDAR fusion as well, and now we're turning to other modalities. So just in conclusion, I think Gaussian splatting and NeRFs can really help to overcome the limitations to sensing and perception that we have in some of these really challenging domains. More work, of course, is needed to extend state-of-the-art to new sensors, which is what this workshop is about. And I think that will enable really exciting new capabilities in multimodal fusion as well, and in downstream tasks, selfishly in robotics. So I hope that we can see a lot of that come out of this workshop too. So just a quick acknowledgement to my students who carry out all of this work and funding sources for work I presented in this talk, and see if we have a couple of minutes for questions as well.
Great, thanks so much. I think we have a pretty small room, so if you do have, I think we can take one or two questions while we swap the speakers. If you do have a question and you feel like you have nothing presenting wise, just raise your hand and shout it out. Otherwise, I think we might have a hot mic over here if you want to walk over. Right, just walk down.
All right, thanks so much. Just a little adjustment here. My great pleasure to talk to you today about some of the work I was involved in, sort of speaking on behalf of my co-authors mostly here. But ever since I was using the first time-of-flight camera about 15 years ago, I had a bit of a soft spot for these types of sensors, for this technology. So today I'd like to present to you several projects that use this technology and look more closely at the sensor data that is used for reconstructing dynamic scenes and also looking into occlusions of static scenes. All right, the first project we called TIRF, time-of-flight radiance fields. This is a novel view synthesis and reconstruction technique designed specifically for time-of-flight cameras. And this was the first paper in a serial collaboration with James Compkin at Brown University and Matthew O'Toole at CMU. And this project was led by Ben Attal, who's also around at the conference somewhere here. And really, it was about exploiting new sensors and the opportunities that they bring. So let's take advantage of what they provide to us and try to sort of improve the depth that we get and the signal and information we can extract from these sensors. So here on the left-hand side, you can see the input that we are dealing with in this project. So we have an RGB camera taking normal video, and we have a time-of-flight camera, specifically a continuous wave time-of-flight camera. And you can see the type of artifacts that you might get in the depth maps from these models. And we're sort of modeling it in a new way to reconstruct better quality depth. Sorry, very superficial here. But the key idea is to combine insights from time-of-flight imaging with neural radiance fields. So there's specific types of artifacts that we see in this depth data. So we get some noisy depth due to low reflectivity. So what you're seeing here is actually there's a black monitor and that reflects very little light. So the time of flight doesn't really get any good signal to get a good depth estimate there. So get a lot of errors there. We're also seeing multiple reflections that give us a bias depth estimate. So there's a shiny fridge on the right-hand side, and you can see the depth does not correspond to the fridge. It corresponds to whatever part of the kitchen is reflected in the fridge. And then third and finally, there's also a problem with ambiguous depth due to phase unwrapping in this technology. So it's using modulated light, and there's only a finite range of depth that is unambiguous. And after that, it's sort of the same phase repeats, but it's not the correct depth. So everything sort of wraps around. You can see here the corridor is too far away. So the depth actually appears to be very close, which is incorrect. And with our approach, we can improve the reconstruction quality and reduce these errors, as you can see here. So in particular, we do handle low reflectivity areas really well. We do handle the multipath reflection quite well, and we do handle the phase unwrapping as well. All right, so most continuous wave time-of-flight cameras capture multiple sequential frames that are combined into a per pixel phase and amplitude measurements. So these are illustrated here. We will dig into the details of the raw frames for a later project, not in this project. But for now, this is the sort of data that we are dealing with. So we have a phase, which is kind of like an angle, but it corresponds to the depth actually of the scene. And we have the amplitude, which corresponds to the reflectance or the reflectivity of the object, or how much light is actually reflected from the object. And unlike previous methods, TIRF explicitly models the rendering of both of these phase and amplitude to help overcome the errors that I showed you on the previous slide. All right, here's some visualizations of sort of how you can think about these amplitude and phase measurements essentially. So what we're working with is phasors. So essentially we are handling both of these together in one complex number. So this is can also be visualized as a vector on a two-dimensional plane, as you know. And the angle of this vector represents our phase. So this is used to recover the depth. And the length of this vector corresponds to the amplitude, and that's the amount of light that is reflected at a scene point. So as the object moves, the phase changes accordingly, right? The object becomes closer, the phase gets lower, the object gets further away, the phase also increases. But we also see as the object gets further away, the amplitude, the length of the phasor gets reduced because less light is reflected back to the sensor. So in the case of multiple reflections, what we're seeing is that we're actually integrating kind of multiple light paths. I mean, the common assumption is that the depth is correlated with the phase. Really breaks down if you have some semi-transparent objects in the middle, because then the depth is no longer proportional to the phase, and vice versa. And finally, for large scenes, as I showed you for the phase unwrapping artifacts, the phase will wrap around at 2π. So if the object gets too far away, suddenly it does wrap around, and it suddenly becomes very close again, or it appears very close again. And we are avoiding this problem with the time of flight depth by construction. So we're not working directly with the depth, but we're working directly with the phase and the amplitude. And as we take RGB and phasor input videos, our goal is then to recover a dynamic radiance field from these inputs using a color and a phasor physically based image formation model. And we optimize the dynamic radiance field by comparing the predicted images to the input with a weighted L2 reconstruction loss. So given enough measurements, we can then recover an accurate dynamic volume, which is good. And there's a few advantages of doing it this way. So first of all, the phasors help in the low reflectance noise, help introduce low reflectance noise. Because our L2 loss is in the phasor space, and it automatically gets smaller for depths that are from these low reflectance phasors. So if the objects are very dark, if they're hardly visible, then it's really difficult to estimate the depth correctly, but also the L2 error will also be lower, and so will be penalized less. So this acts as a kind of confidence applied to the time of flight depth estimates, and lets us fall back on triangulation in these cases. And I say triangulation because the camera, the RGB camera and the time of flight camera are not in the same position, but the dynamic nerve reconstruction that we are reconstructing has to be consistent, has to have the density in the right place for both sensors, essentially, so we can triangulate the density that way. And we never explicitly penalize the depth that is derived from the time of flight camera, because we're only working directly with the phasors, and that avoids making any hard decisions about the depth. So as such, the density can be placed at multiple points along an array, and so as long as the phasor sum matches the measurements that we are observing. And third, we're sharing the density between the time of flight and the RGB camera volumes, essentially. And that also helps us prevent the phase wrapping errors, because it has to be consistent for things that are parts of the scene that appear further away. Let's look at some results and some comparisons here. On the left-hand side, you can see the input that we're working with. So this is a single moving camera, RGB camera, and a time of flight camera that we are tracking. With TURF, our method, we can reconstruct the dynamic scene quite accurately. We can reduce the errors due to the low reflectivity, as you can see, for example, in the ice maker machine on the left-hand side. And other methods like VideoNerve, for example, struggle with reconstructing consistent depth. Here's some more examples on the specific examples that I showed you earlier for the depth errors that are observed with the vanilla depth that comes out of the camera. So here you can see the dark monitor, and really difficult to estimate the depth there. But this is where the visual camera can also be useful for constraining where the depth actually is of that monitor. So with TURF, we combine the benefits of both and reconstruct a more accurate geometry throughout the scene. And here's the scene where the distance, where you see the phase wrapping artifacts on the left-hand side. So the corridor is too far away, and the phase wraps around and appears very close. And with our approach, we can unwrap this correctly, whereas other dynamic nerve approaches such as video nerve that are trained directly on the depth that comes from the sensor obviously cannot overcome this because they do not know what to do with that. They assume the depth is correct. It's not correct. So you sort of have the situation of garbage in, garbage out in this case here. And we can also see that our approach nicely handles the multipath interference or the reflections. So you can see the nice reflections on this glass door. And you see the depth also being consistent with what you would expect it to be. All right, in a follow-up paper then that we called Float, time-of-flight radiance fields, we addressed another key limitations of continuous wave time-of-flight cameras. So they assume that all the raw frames are actually captured at the same time, which is not the case in practice. It does work for static scenes because you see the same content for all the raw frames. But whenever something moves quickly, such as this pillow that's getting dropped here, you can see there's a lot of depth estimation artifacts here because the pillow actually moves and is in a different position for each of the raw frames. So this is another collaboration with the same set of people. Mikhail Okunev and Mark Baker were leading this one on the Brown side. All right, let's look very closely at what's happening in an ideal continuous wave time-of-flight sensor setup. So we have a laser or an emitter that emits light into the scene in a sinusoidal pattern, and then you capture the raw frames from the return signal. So this signal is sinusoidally modulated. So we are seeing different intensities at different capture times as the signal gets reflected back to the sensor. And this is fine for static objects. I will not go into the math here. But what we're seeing is if the object actually moves, so we're capturing all the raw frames at different time instances, the object sort of moves under the pixel that is being considered, is being looked at. So same pixel does no longer correspond to the same depth for all the raw frames. And this introduces a disparity across these camera frames. And the depth you would get from that, using the equation I showed earlier, would look something like this. So this is quite severely corrupted compared to what we would like to see. You can see the background obviously looks great. That's a static scene, right? So everything works great there, but all the dynamic things have severe artifacts. So the way we're going about handling this is to actually use this model of a 4D dynamic scene and try to learn that like a dynamically changing radiance field, and then try to explain every single raw frame at that time instance and how it is represented. All right, I guess you got to show some equation with an integral here. But what we want to do is to recover the unknown scene essentially by optimizing for the rendered raw frames, I guess the captured raw frames. All right. What's kind of the neat insight here is that with this function phi that we have in the middle, we can use different sinusoid phase functions to recreate sort of the appearance at the different time instances. So these are for the different phase shifts of the original emitted signal. And so we can render the dynamic scene at any time instance for the specific corresponding to the signal. And that actually provides a lot more supervision data to reconstruct like a time super resolved dynamic scene. Okay, so normally, like you probably know that you supervise at every time step. That could be quite difficult because, as you see, they look very different, these raw quads. So we couldn't use optical flow for correspondence between them, for example, because there's no photometric consistency over time. So we do need to have a better way of actually rendering and recreating this sort of appearance change. And that is what we call the, what is it? Phase invariant reprojection loss. And what we can do then is we can then, once we have the dynamic scene reconstructed and supervised at the subframe time steps, we can actually also render the whole scene for all 4 quads and sort of synthesize the quads at that time instance. And then once we have these quads, we can actually then compute the depth correctly for that time instance. So here you can see what the difference looks like. At the bottom is the incorrect depth estimate based on assuming it's a static scene essentially. And on the top, you can see our depth estimate that is much more accurate here. Here's a real scene that we captured. I mean, it's still in the lab, but it's a real scene. And you can see, if you look at the dashed line at the top, that the ground truth assumes these frames are synchronous, they're taken at the same time, but actually they're not. The pillow is dropping, so the same corner of the pillow is not in the same position in the image space for all the 4 different raw quads. But with our model, once we have it reconstructed and rendered, we can synthesize these 4 raw images, and you can see the corner is aligned, so the depth is seen in the right place. Here's a comparison between the input, which looks pretty rough, right? Then the turf paper that I presented first that handles the phase unwrapping, so that's nice, but it doesn't handle the fast dynamics. And with the flow turf, we can handle the fast dynamics quite accurately, which is very nice. And one of my favorite outcomes of this paper was really that we can also do scene flow interpolation over time. So we can do like 8 times temporal super resolution and almost do like slow motion. So at the top, you can see that is the frame rate you will get from the time of flight camera. And sometimes there's just a few frames of animation for the baseball bat, for example. And at the bottom, we have the 8 times temporal super resolution. So we can do like a slow motion animation of the bat being swung. So qualitatively, this is great. It's just super slow because it's based on NERF. And so at CVPR this year, we're presenting a version based on Gaussian splatting that we creatively call the time of the flight of the Gaussians, optimizing depth indirectly in dynamic gradient fields. And that's led by Ron-Fong Lee, who's presenting the oral presentation on Sunday morning. And here, we're sort of extending the work that we've done with neural radiance fields and use Gaussian splatting for speeding it up. But obviously Gaussian splats also behave somewhat differently. There's no notion of a field anymore, really. So you have to sort of try to get the Gaussian splats in the right place on the surfaces. So here's a reminder for the fast motion. You can see these artifacts that are coming from that assumption that all the raw frames are captured at the same time instance, which they are not. And then with our approach, we can now actually also track the Gaussians. So this was something that was also would be really quite difficult to do, or you would have to use the scene flow field for tracking it. But here, since we have explicit Gaussians, we can also track them and visualize these trajectories quite nicely. And the way this works is based on a variation of 3D Gaussian splatting. So as a quick reminder, in Gaussian splatting, we have a bunch of Gaussians, and for each pixel, we're looking at the Gaussians that are overlapping one ray, and they have a color, they have some weight, and they have some second weight based on the transmittance, on how much was already observed. And these are all accumulated across a few different Gaussians from back to front, so that we can render the color of a particular pixel in a scene. And so the way we are then modifying this is to taking these Gaussians and extending them to the time of flight, the CTOF, the continuous wave time of flight imaging model. So here we now have an emitter. So previously we sort of assumed the Gaussian splats would emit the light and we just capture it with the camera. Now the light actually comes from that emitter. It is sent into the scene, it interacts with the Gaussian, and then the light comes back to the sensor. And so a certain amount of light arrives, which is very much dependent on where we are in the sinusoidally modulated signal that we're sending out. And then, this depends on the depth as well, because there's also distance squared light fall off, and then the light obviously has to come back to the camera again. So that's the returning ratio, and the rest of the model is very much the same as in 3D Gaussian splatting. So we have a weight and the transmittance, and we're accumulating all of these over all the different Gaussians that we're rendering. And accumulating all that gives us the raw time of flight return. Now, unlike with the NERF, what we can do is we can, if you render these quads, again, so on the left-hand side is sort of the capture from the camera, the raw data, and the right-hand side is where we can recreate, where we can render based on the reconstruction. And yes, you can match it very well, but the surprising thing really is that the depth actually is not very accurate there, because the Gaussian splats, they can cheat a lot. Again, we don't know exactly where they are, but as long as you accumulate and you sort of reproduce the raw quads, there's no guarantee that the depth is actually accurate. So this is what we're seeing here on the left-hand side is the depth you will get from the camera, again with the standard errors. On the right-hand side is what we get if we compute the depth the same way from our reconstruction with the Gaussian splats. So we get the same sort of artifacts and issues. We don't really solve anything here. Now, if we take the Gaussians and render them, render a depth map directly from them, this is what it looks like. And you can see there's a lot of glowing stuff going on. There's a lot of floaters. They're all in the wrong place. So we found that we need to adjust the training and better deal with, in particular, with low reflectance Gaussians. So how do we do that? We're sort of trying to initialize the scene in a slightly smarter way. And what we looked at first is the sparsity along array. So where are all these Gaussians? We would like to see the Gaussians being very compact in space, so we don't have a lot of overlap, a lot of depth uncertainty. So we're trying to regularize this to, we're adding a distortion loss. We're also having a lower learning rate for the reflectivity so that it's sort of, that the Gaussians are preferably moving in space rather than just getting darker to simulate that they're moving further back. So it's sort of tweaking the learning rates there so the Gaussians move in the right way. And then finally, we're also initializing sort of with the low reflectivity first, assuming a distance scene, and then the Gaussians slowly come forward, and slowly the amplitude increases. And the results look fairly similar to the turf results. The depth is accurate, as accurate as the F turf. It is more solid looking, and so the key thing also is that this is now 100 times faster to train and to render. So that's super nice. Let me quickly move on to another project that uses a different type of time-of-flight sensor. So this is using LiDARs. And this is a collaboration with an intern, Sophie Klinghoffer from the IT Media Group, the Camera Culture Group at the Media Lab. This was a paper at CVPR last year and actually one of the award candidates. And what's really cool about it is it can figure out what's in that chair, because we don't know what's in that chair. It could be empty or it could be some object in that chair. But with the LiDAR, we can actually reconstruct the scene. We can reconstruct the density where we can't see things, because we can reflect light into the scene and then reconstruct where the light rays get occluded. So LiDARs might seem like some sort of exotic sensor, but really chances are you have one in your pocket if you have an iPhone or a recent Samsung phone. And these LiDARs are becoming a lot more widespread also in mixed reality headsets, in autonomous driving. And usually they're used to get some depth information, but we can also get more interesting information in the sense of we can get shadows. And this is where the name of the paper comes from, like from, we call it Plato nerf. So we can reconstruct the scene based on the shadows that we're seeing on the sort of the side of the cave. All right, very quickly here, we have a sensor and a laser, and the laser shoots a ray of light into the scene. And the first return, this first bounce, is giving us the depth of the scene. But then the light continues to bounce around in that scene. And these second bounces is what we are exploiting in Plato nerf. These second bounces can tell us a lot about the structure of the scene. You can see the light propagating here in the scene essentially over time. And with that, we can reconstruct the geometry, the density of objects that are not directly visible. All right. So yeah, these are some of the results that we achieved. These are quite nice. And a very quick look into some other type of non-conventional camera. We also worked with capturing the audio in an environment as well. So we have audiovisual spaces that we worked on. This is a project from last year's CVPR called Real Acoustics Fields, where we densely captured an environment, both with lots of camera images, but also with lots of sounds that are captured, emitted from a speaker at known positions in 3D space, and then captured at this tower of microphones in other locations to capture and recreate room impulse responses. And based on that, also at CVPR, we are presenting Sound Vista, which is a novel view ambient sound synthesis technique. This will be presented on Friday. And with that, I'd like to thank all of my collaborators who made all these slides, who made all the work. And as I mentioned, the Gaussian time-of-flight work will be presented on Sunday in the Sunday morning oral, and the Sound Vista paper poster will be presented on Friday afternoon. Thank you so much for your attention.
I think we can take a couple of questions. We have a couple of days well, so.
Will you say a little bit more how you handle the multi-bounce? Like how do you get rid of the first bounce and focus on the second one?
Oh, that's a very good question. You got me there. So in this method, it is sequentially scanning different points in the scene. So we do know the location of the 3D point, and we do know we have the full transient, like the time histogram of the recovered response. So we can discard the first bounce and look at the second sort of peak in the response and see essentially where do we get this from, so that it that we can reconstruct. So we know sort of the geometric calibration of the sensor and the laser, and we sort of get this triangle and we try to figure out where is that second bounce point essentially. And in particular, what is happening between these two bounce points? Is there something that's blocking the light? So are we expecting a response from that second point and we're not seeing it? Because then it's blocked. Then we know that there's an object there somewhere. But if we see a response, we know that it's free space. So this is how we can.
Very much bounces, multiple reflections back, and then you're using that.
It's like in a different location, I would say. So the light comes in here, and the first bounce comes from one particular direction, and we have that calibrated, so we know where that is. And we then look everywhere else in the image essentially and see where the second bounce is coming from.
I'm gonna steal a screen share from you, but you can still answer one more question.
Thank you very much for inviting me. I'm Jingyi Yu from Shanghai Tech. And today I'll be talking about NeRF beyond the regular radiance fields and talk about physics, world models, and beyond. I was actually planning to give the talk in person, but due to a last-minute conflict that I couldn't come in person. Everybody knows about NeRF. It's a differentiable rendering primitive that fits perfectly with the neural networks. And but very interestingly, it's also what I call a holistic representation. Holistic in the sense that in multiple ways. First is that you can actually capture the object from different perspectives, so you can view it omnidirectionally. And the second, which I'll talk later in this talk, is it's a very interesting combination of understanding and generation, but we'll leave that later. Many of people probably did not foresee the coming of NeRF, right? So why NeRF emerged in 2020? In my humble opinion, is that it largely attributed to the hype of virtual and augmented reality during that period. Remember around 2015, everybody was talking about the volumetric capture because they see the possibility of VR and AR. So people view domes, for example, we build domes at Shanghai Tech. And with the mobile phones, you can actually capture an object from omnidirectional viewpoints, right? So you can capture objects very conveniently. This actually gives birth to, in many ways, in my opinion, to NeRF. So, but in the past few years, right, multiple representations, new representations emerged. They realized that we do need a continuous representation that's differentiable, but continuous doesn't mean it has to be a neural net, right? So you can actually use 3D Gaussians or a tensorial field to represent the 3D volume. So my student Anpei Chen invented this tensor, and 3D GS is so popular everywhere these days. So this chart shows the kind of the evolution of 3D representations. On the left, it shows deterministic representations, polygon meshes, points, etc., etc. On the right, you see the Gaussians, triplanes, and even latents. These are stochastic representations. And these representations kind of form the spectrum today on how we represent the 3D world. So I start with saying that neural radiance fields actually goes beyond the radiance. You can capture more than density and the color. For example, in a broad range of applications, you can try to recover normals, transients, absorptions, etc., etc. So the first project we did is trying to recover specular fluid surfaces. In this case, we discretize the volume, and at each voxel, we try to recover its density sigma and also its normal. Then you accumulate the normal along the observation rays. It's worth noting that similar ideas have been proposed at this year's SIGGRAPH, but in the Gaussian sense. For every Gaussian sphere, you can actually not only try to recover its color, but also its normal. And you can accumulate along the rays as well. It's worth noting that multi-view capture is actually very common in medical and biomedical imaging. CTs, MRIs, cryo-EM, cryo-ET, they can all be viewed as multi-view capture. In other words, radiance field, the neural radiance field type of representations can be potentially extended to these medical imaging applications. But before I dive into the medical part, I'd like to try to talk about neural transient field. So for this audience, you are very familiar with non-line of sight imaging. And essentially, you shine a laser onto the relay wall, and each scanning point on the relay wall serves as a virtual camera. But in this case, it's different from traditional light field or planoptic camera, because every scanning point, you're collecting transients along a 2D spherical wavefront. Therefore, your integration is not along a 1D ray, but on a 2D wavefront. So in that case, you have to discretize the spherical surfaces, and the computational cost can be much higher. So to address that, in our PAMU paper, we basically proposed something called hierarchical sampling, and trying to reduce the sampling along the spherical waves so that you can actually reduce the computational cost as well. And here are some sample results, showing that it's particularly useful for recovering, surfaces or objects with different depth layers, and as well as it can reduce the number of sampling and achieve comparable quality. So, but in any case, it shows you that you can use a kind of like a nerve of settings. But you also realize that the NETF shows you that you have to follow certain type of physics, right? You cannot just do the regular nerve rendering, meaning that you're like integrating along array. You have to change the physics behind it. So the second topic I'm going to talk about is how do you integrate the physical constraints, right, into these neural field representations. So in other words, beyond the regular using MLP to do kind of like a color and the density inference, in this case, color can be anything, you have to also add a physical model layer, right? And to match your observations. So I'm going to give you a couple of examples, one from medical imaging, two from medical imaging, the other from physics. So let's come back to the problem of CT scan or MRI scan, right? In this case, it's a CT scan. So for those of you who have done CT scan, you may think it's a very easy thing to do. You can do the kind of the Fourier transform and using Fourier slicing theorem to recover the volumes, right? But the very important thing to notice is that human tissues are truly constant or almost constant observations. This kind of like human tissues are more nerve type of assumptions. But what about the human tissues that has metals? For example, your bones has a metal nails, something. So in that case, if when you're doing metal scanning, for example, you have a dental implant, metal dental implants, you do the CT reconstruction, you will observe on the left something called the ghosting artifacts. And the ghosting artifacts is mainly because of this nonlinearity metal effects, meaning that it no longer follows the regular nerve or volume rendering equation because it's a nonlinear degradation. So how do we handle that? So the idea is pretty straightforward and highly effective. So in this particular case, you can assume that you have X type of materials, right? You can assume you have bones, you have flesh, you have metals, certain type of metals, different type of metals, and you may assume that kind of the material is a combination of them. So in this case, then you are actually changing the regular nerve formulation into a combination of different materials. And then these materials can each be modeled with a distribution, okay? And then using the similar formulation, you can actually set out to not only recover the density, but more precisely the combination of these specific densities to achieve the minimum loss. And this turns out to be working amazingly well. So for example, we can use that to do metal artifacts, removal. On the left, you see actually weird, ringing and, scanning the radiating artifacts due to this nonlinearity. This is using traditional methods. In medical image, they have all kinds of like traditional tools to handle that. But for when you meet with the metal artifacts, they're kind of doomed. It's like you can't very effectively to suppress them. So what we did is that using this kind of NeRF representation, but a small tweak, right? Because we add on some material priors and describe using this material priors to describe the absorption model. And then the formulation try to characterize the linear combination of these material models trying to recover the actual material. It removes the artifacts significantly. You see the improved reconstruction significantly. Oops. Another project we did with the medical imaging community is actually trying to recover motions. So when we do CT or MRI scans, and in particular, for example, MRI scans, right? It's a very slow process for those of you who have done MRI scans. We have a couple of MRI machines at our university. We try them all the time, and you'll find that you have to keep very still. For those of you who have done MRI scanning, you have to keep still, very, very still. So when you move, then you will induce certain type of motion. And how do we compensate that motion? And the approach is amazingly simple. So you add one more unknown. You assume that there is one more spatial transform before the images are fed into the MLP to do in this case, it's the absorption recovery, right? Absorption recovery. So you try to recover both the kind of the transform and the volume reconstruction. So if you've done like ST nerve or a spatial temporal nerve, it's kind of the similar idea but adopted to the medical image domain. And simply by doing so, you will find that the resolution of the final results improves significantly. And this is very simple but very, very effective. And very interestingly, this is unsupervised. So this is like for medical people, right? If you have unsupervised neurorepresentation, this is amazing to them, right? Okay, so we'll talk a little bit about the CT MRI. Then we started looking at ultrasound. Can we do ultrasound? Because as long as this is a multi-view capture system, right, you can potentially use neural fields type of representations. So this is a collaborative work with ultrasound faculty members. But one thing about ultrasound, different from CT or MRI, is that it's trying to capture the time of flight, right? Capture time of flight. However, the major difference is that the path of rays in this case. So in the regular nerve sense, the rays are their straight lines, right? But because of the heterogeneity of the materials, in this case, sound will propagate nonlinearly within the tissue. So in other words, you have to account for this nonlinearity of the path. So our work is or traveling path, right? So the approach to that is pretty simple. So you do kind of an iterative approach. So you try to first estimate the volumetric reconstruction. Then you you first assume this is a linear path, right? This is kind of straight lines. But once you obtain the initial estimation, then you do kind of the path changing. You want to find the shortest path with the current estimation. Then you re-estimate the path again. So it's kind of iteratively estimating the curved path of how sound propagates through the tissue. And it's actually in density. So you do this iterative process, and we have shown, this is published at the ultrasound journal, and this is showing that you can actually greatly improve the final reconstruction, reducing aliasing artifacts by a large margin, particularly when you have a sparse number of samples. So this is also amazing for nerve. We find that sparse sampling is particularly suitable for nerve if you have a physical priors. It works way better than any other traditional methods. And one more example that we tried with a nerve using, for example, optical tomography. So optical tomography means that when you shine the tissues with a laser, then it will actually kind of diffuse into a disk, right? It will scatter through the tissue and then emits out. So this is again different from the previous ultrasound one. Ultrasound one simply just a curve we call bent ray. The rays are bent, it's a bent ray nerve. But this is a scattering nerve. You have to scatter the rays. So, but simply enough, there is the underlying equations for telling you how the rays are scattered. At least can be approximated to scatter the rays. So once again, we formulate the problem similar to the ultrasound. We do this iterative improvement. First, we do the initial estimation of the density field, right? Then we try to compute from the density field how the rays are scattered out. But computing that is expensive. So what we did is that we first model use a finite element model. We compute the density field on the finite element, and then with the finite element, you can compute how the ray scatters across the tissues. And once you do that, you do this kind of iterative optimization, try to find the further refine the actual volume. And this is showing you some of the reconstruction results, right? So on the left, these are like real results. These are translucent objects. You have some kind of patterns embedded in the translucent objects. On the right is some experiments, for example, capturing, our brain blood vessels. And you can actually see using this column we call neural DOT, optical tomography, that you can actually recover highly realistic, very high quality, tissue trees. You can see the blood trees, right? You can see the blood vessels. They form kind of a tree structure very clearly. You can even do the slicing because of the volume nature of nerve. And finally, we also did something with the physics department, physics school here, where we do atomic scale on neural fields. So in this case, the goal is trying to use a TEM to observe what TEM refers to transmission electron microscope, to observe the materials. And the goal in this case is not to recover the density because it's meaningless. You're recovering the phase and the amplitude of the wave at this layer of material. So different from previous tasks, previous tasks are all volumetric reconstruction. You want to recover the density or whatever all within a volume. In this case, you only assume it's a very, very thin layer of material. So you're recovering one single layer. But your observation is that you change observation plane, because if you, for those who have used TEM, you're like doing kind of confocal scanning, so you're changing the focus, and then you measure the defocused image from the TEM. Then you formulate the problem as you recover the amplitude and the phase of the thin layer, and trying to once again use this MLP structure. And experiments show that actually it's can recover very high defined details that are generally missing using traditional methods, right? And you can see many of the details, especially through slicing, can be recovered. Then you can recover the three-dimensional structure, lattice structure of the material very accurately. So this is showing you another case. All right, I think I've shown you two aspects of my talk, showing you that you can use neural fields to recover beyond RGB and the density. You can also use neural fields to do more tasks, as long as this is a multi-view capture. The multi-view capture can be, CT capture, it can be, TAM capture, can be whatever capture, as long as a multi-view capture, you can use that kind of scheme. But I want to spend some time on the last part of my talk, which I think will be interesting to you. That is neural fields and the foundation model. So, for example, for those of you who have done, a non-line of sight imaging, right? We know that non-line of sight imaging is effective, right? It can capture some of the occlusion part, right? But also, the scanning process is very painful, because you either have to scan very, very densely on the wall, right? Then you can recover the hidden objects. And also, if you do a like front-on scan, right? Meaning that if you see most of the NLOS imaging system, right, they have to scan the scene from the side, right? Because front-on, you will cause self-occlusions. The object itself is occluding the scanning patterns, right? So if you want to scan from up front to see the back of an object, it's generally very challenging. You can only get the sparse sampling. All right. And in the past 2-3 years, right, significant advances have been made in world models, in particular in 3D generation. My own group, are lucky enough, to receive the SIGGRAPH Best Paper Honorable Mention last year for our 3D generation work called Clay. And the Clay is a 3D generation model. And the goal is kind of by saying that if you only see the front image, can you generate the whole 3D shape out of it, right? And after that, a number of works, have followed the Clay, including Triple, including Tencent Hunyuan, and they all try to improve upon Clay. At the core, but if you think about what Clay does, or 3D generation does, right? One way to think about it is guess what the back looks like, right? So you look at the front, can you tell us, what the back object will look like? So this is quite interesting, right? So let's look at, the transient imaging again, right? So in the transient image, right, it's trying to partially to recover the back of the object, right? The goal is trying to recover the hidden part of a specific object, right? Okay. So in order to handle that, right? So you can actually use, for example, measuring time of flight, blah, blah, blah. But what's important is that in traditional 3D generation, you are looking at the front. In NLOS image, you are looking at the back. So in other words, if we are managed to put them together, we are actually capturing a holistic image from front to back, right? So the front is a RGB image. From the back is some kind of transient measures, maybe not very accurate. So at ICCP, last year, and also PAMI, so we developed this approach called the Holly 123, holistic image to 3D, Holly 123. The idea is you use the front image as image supervision. Then you use the back transient as the back constraints or back prior. And then you do the 3D generation model. And this is showing you the pretty cute part, So if you're only using the front view to guess what the back will look like, right? So on the left, this is Pokemon. You will see that the back will be wrong. But if you're adding just a tiny little transient signals, tiny little NLOS signals, you'll be able to capture the front and the back accurately, right? On the right, it's showing you the Ninja Turtle. And again, you'll see if you're only using the front, then the stick will be missing, right? But if you use Holly 123, by just adding a little bit of back signal, a little bit hidden signal, you can actually recover or generate the 3D scenes much better. All right. So this is showing you that kind of like how NLOS imaging can help with this 3D generation. By the way, the 3D generation pipeline follows again using the neural radiance field. Okay, neural transient field. But the problem is also the opposite. Can you actually use the foundation model or 3D generation to improve non-line of sight imaging? Okay, in other words, right, if you are like, in other words, right, if you are like capturing the NLOS image with a very sparse set of sample points, very sparse set of sample points, but if you train a model kind of that takes the sparse signal as input and guess what it will look like. So in other words, it's like a 3D generation on NLOS. So let's dig a little bit deeper on how 3D generation is done. So in the Clay paper, like I mentioned last year at SIGGRAPH, right? The main idea is a couple, right? First, we introduced a geometry encoder. Basically, in this case, we use a vecset representation. And then we train, to establish attention across different positional embeddings. And the second very interesting thing is it's the first paper that introduced the diffusion transformer. So you use a diffusion transformer to do the 3D shape reconstruction or generation. Before us, diffusion transformer was mainly used to handle videos, but in our work, it's mainly used to handle 3D, vecset field. And the most important part is that we also use image supervision. So like I said, the input is a front image, right? In this case, we use the dyno feature from the front image and trying to supervise or control use as controls, right, to do the 3D generation. So these are the three key components. So if we want to use that for non-line of sight imaging, right? So we need to do similar things, right? However, it's very important to note, right? There is no large data set of non of sight objects. So the first thing we did is that we constructed like 500,000 3D objects from Objectverse. And then we build which we call transientverse, a data set that, kind of like used for training or representing the transient field of the objects and use that and a similar pipeline. So in the this approach, so we basically, again, using similar ideas from computer vision, we use the masked autoencoder, okay, MAE, for NLOS reconstruction. And I'm not going to dig into details, but essentially, because we're looking at a volume, right? The transient is a volume, right? So we're doing the volume. We basically partition the volume into, blocks. Then we mask them out, then train a network. Why is it important? Because our goal, remember, is from sparse NLOS signals, can you recover the shape? Can you generate the shape? So the masked autoencoder is a perfect arena for doing that, right? But with a sparse input, if you are pre-trained a world model, you can recover the object very efficiently. So this is showing you like a very simple example, even with 5% sampling, you only train 5%, you can actually recover the quality as if it's 95%. So this is a pretty amazing results. And this is a number of other objects. Using very sparse sampling, you can recover the dense image sampling, dense sampling points. The dense sample the transient signals. Then once you've done that, you can use any other methods like LCT or PF, whatever, to recover the actual 3D objects. So it's a perfect way to do upsampling from sparse sampling. All right. So we've come to the end of my talk, and a parent question is like, we have NeRF, we also have 3D Gaussian. Where does it go? Which one will win? To me, it doesn't matter. Because what matters, I believe, is the holism or the bridge between generation and understanding. So no matter it's Gaussian or 3D GS, I think the future is going towards a bridge between understanding and generation. The examples I've shown on the NLOS case, we've shown that if we have the foundation models, we can understand the scene better. Then we need the sparse sampling. The Gaussian or NeRF representation will be simpler, and the vice versa. To that end, I point out to our SIGGRAPH paper this year called the CAST. This is the first paper that understands the 3D scene using or generate the 3D scene from an understanding perspective. We understand the relationship, then we try to generate the scene from images. There are other interesting directions. First is the graphics hardware. So we have all kinds of graphics hardware for 3D Gaussian, but we still don't have graphics hardware for radiance field. So in the past few years, we have developed a new hardware called the graphics generation unit tailored for radiance field. This is showing you that actually using this kind of like hardware, we can actually doing rendering in real time on this tiny little chip. And this is a very low power chip to do neural rendering. And I believe this can be very useful. By far, we are mainly dealing with object-oriented neural fields. But in the future, I think we're looking at environment or large-scale neural fields. And finally, most of my talk focused on static neural fields, but the future will be dynamic. And it has been my dream to think about how to capture dynamic, for example, CT images. So if we are going to capture, volumetric CTs, then you see how the bones move, how amazing that would be. So to this end, we at Shanghai Tech built the first biplanar X-ray system. You see the two planes. Each plane will capture a X-ray video of an object. And you see we're capturing X-ray video from different perspectives. This is showing you the X-ray video of a mouse moving. This is probably for the first time in history, you see how the inner bones moves. It's real, right? It's not human labeled. It's a real mouse bone, how their joints move in 3D space. So with neural fields, we expect this can complete the picture to do volumetric reconstruction. And this concludes my talk. This talk is largely attributed to a group of very talented colleagues and students of mine from medical imaging, biomedical imaging, and computer graphics hardware. And thank you very much for your attention. I invite you to come to Shanghai Tech to look at our dome system and our X-ray biplanar scanning system. Thank you.
All right. Cool. I'm Yomin from Cornell, and I'm presenting our recent work, self-calibrating Gaussian splatting for large field of view reconstruction. And this is a collaboration between Cornell, Netflix, and also Stanford. So reconstruction is actually a very long-standing problem, and before you can get a reconstruction result, you have to do some kind of captures. And you can see on the left is actually Paul holding the camera and help us to do with some captures. But it seems that our human beings actually super efficient for the reconstruction. And by simply walking around, and we can actually map something and also have a very rough understanding and geometry of the whole things. So it comes to a problem that how can we actually do that? Of course, our human being, our brain is super intelligent, and also we have some kind of 3D priors in our brain. But I think most people actually take it for granted that we actually have a super powerful sensors, which is our human eye. And just in case you guys don't know, our human eye field of view is actually approximately like 200 degree field of view, which is significantly larger than the regular camera. So that's also one reason that we can actually do such efficient reconstruction. So actually, I think probably inspired by this, so people develop some specific kinds of camera, which is the wide angle camera, which I show on the right. So you can see with different design of the lenses, you can have a very different field of view, from like 120 all the way to 150, or even over like 180, which means you can actually project something on your back. Yeah, And also, if you notice that in that video, in the first video, Paul is actually holding a camera rig, and this is actually some kind of 2 wide-angle camera and actually positioned perpendicular to each other. So it's kind of like simulates our human monocular, like actually binocular vision system. Unfortunately, even with such like efficient and powerful sensors and cameras, we cannot actually get a very nice reconstruction result with current pipeline. And here's the example for Gaussian splatting. So we just simply combine the captures like raw input, and then we do some reconstruction, and we transfer from the raw input into something that Gaussian splatting can handle. And then the output looks like that. Which is not perfect. You can see a lot of holes and black area. So why we got this? So for the past decades, so what people actually use such wide angle camera is very interesting. So actually people use a fixed camera model. And what people will do is that they will do pre-calibration to estimate this camera model's parameters. And after you get the camera model's parameters, you will need to use those parameters to undistort the images into perspective ones. And then you use those perspective inputs to do some reconstruction, maybe fitting to like nerve or Gaussian splatting. But you will but one problem for this is that you have to do pre-calibration, right? So the way you need to do that, especially for a large field of view, you have to place like checkerboard probably in the whole 3D space, and in order to cover the whole field of view, which is actually not feasible. And also sometimes you only get the images, so there's no access to the camera. Also, that's another problem. And even though you got those camera calibration and also camera parameters, another things or another issue that introduced by undistortion is actually, you can see it in the middle, which is here when I visualize undistortion. So basically the left is raw input and the right is perspective images. So if you undistort more field of view, when they're getting close to 180 degrees, then you will see the stretching on the bottom, which is not very good input for the current reconstruction pipeline. But of course, you can do some cropping, like you can do this blue one, which is like you only take a very central part of the raw image and then undistort it into some kind of input that you can use for the Gaussian splatting. But actually, that's kind of contradict to the very purpose of wide angle camera, because if you have such wide angle camera, why you just crop it out? You can use all the information instead of crop out of peripheral regions information. So essentially, our method is actually trying to handle both issues. So first of all, in order to get rid of this pre-calibration and also the very inaccurate calibration, we propose to replace traditional distortion model with a hybrid distortion field, which can kind of be a plug and play module that you can use in the reconstruction pipeline. And also, in order to handle this single planar projection, which is like undistortion problem, we propose to use cube map projection, which can actually handle the stretching problem so well. So let's get into the details of both these designs. So first of all, hybrid distortion field. So we propose to model distortion in 2D space, which means you essentially just use a neural network to predict you move the 2D Gaussian around and make them to match with the pattern of distortion. So it's kind of like a simple idea, but unfortunately, because we use Gaussian splatting as a representation, so typically a single thing can be probably several millions of Gaussians to represent the whole things. So it's very computationally expensive to kind of move all the Gaussians with this neural net. So instead, our solution is actually we propose this hybrid representation, which combines the neural network with some kind of control point. And high level, the idea is simple. Basically, you put the control point or control grid into 2D space that that 3D Gaussians are projected on, and then you basically feed all the control point into that neural net to produce that distortion residual. And then whenever you need to kind of figure out, okay, if this 2D Gaussian should be moved around or not, you just simply do bilinear interpolation between probably four, actually it's four control grid, and basically you use the residual distortion to do that. And here's the comparison of our method with vanilla Gaussian splatting, which never considers the distortion. So you will see the floatering and inconsistency. And also another baseline is just simply use the conventional distortion model, which we're trying to illustrate that even though, as you can see at a very central part, they did a good job, but for the peripheral region, you can see the consistency and some kind of very spiky Gaussians. So we believe that's from two sides. One is the traditional representation is not good enough. And the second is probably because the distortion parameters estimated by probably like COMAP or when you do the calibration is not accurate enough. Yeah, so let's get into the second part, which is the cube map projection. So actually, in order to avoid that stretching, we replace the single planar projection with a cube map. So essentially what we do is simple, like first, we do rasterization, which is you take all the Gaussians and rasterize on the 5 faces of this cube. And then whenever you need to do this final rendering, and here I have a visualization, which is a purple like rectangle, that's the final rendering canvas. So whenever you need to render some pixel on that canvas, basically what you need to do is just to find that point, and then connect to the camera center. And then you have the intersection with the cube map faces, which can enable you to kind of avoid that stretching. So we want to illustrate that actually wide angle camera is very useful for reconstruction. So here's a comparison. So we use 200 views, but we use regular camera to run Gaussian splatting for the reconstruction, while we only take like 20 views for our method, which we use a wide angle camera. So obviously, each per capture can have a very large capture if you have a wide angle camera. So actually, you can see we got a more complete reconstruction. So for fair comparison, we also have a same camera pose distribution. So that's actually the only difference is actually the numbers of captures. And whenever you finish the optimization, you can render whatever you want. So basically, if you want to render in small field of view, then you can render it in real time. And if you want to render like 360 panorama, then essentially just kind of renders all the faces of cube map and then do resampling, which is still real time. And of course, you can do fisheye view rendering, which just look on the right. And here I draw a small circle. And this circle is actually means the 180-degree field of view. So that actually means we can render something on the back if you can design some kind of lenses that projected something on your back. So that would be a very powerful tool to use for reconstruction. I think that's almost the end of the talk, and we don't have time for. Okay, cool. But if you guys have some question, you can catch me later, and feel free to scan the QR code to see. Yeah, maybe just click the link on the website. Thank you so much.
For the technical difficulties. Hi, everyone. My name is Sage, and I'll be presenting our work on neural refraction fields for image verification. So it's well known by now that AI-powered image synthesis and deepfakes are making image manipulation very commercially accessible. This generative fill tool allows for image splicing while maintaining coherence with the surrounding environment. And we also have video editing, deepfake tech. And in this paper, they showed that humans got something like 48% accuracy trying to distinguish real from StyleGAN2 synthesized faces. So image forensics or image verification has emerged as a field to combat these risks. And I'll very quickly just mention that there's more physics-based analyses where especially models like DALL-E 2 Paint by Text, for example, don't explicitly incorporate these fundamental geometric principles into their modeling. And then there's more data-driven analyses where you can compare statistical distributions of real versus fake embeddings. So what can the subject of the photo do to actually protect themselves? After all, they don't have any control over the person taking the picture. They don't have control over the software, the post-processing. They can only control what's physically in the room with them. And they can only interact with the software via the photons that bounce off their body indirectly in some way. So maybe let's place like some glass decorative object in the room, and maybe we can detect manipulations by looking at it and seeing if the refractions check out, if they're consistent with the recordings of the room. So say some Nashville loving troll comes in who maybe really has something against Ohio, and they manipulate the image. How can we verify the truth? Well, we can take a look in here, and if we just take a look at the right location, we can find that there's some geometric inconsistency in the refraction and the broader picture. And so that can allow us to detect manipulations. So this approach was actually already introduced in a prior work called Totems, where basically you have an image and you physically embed these glass spheres sort of acting as natural watermarks in the image. And what you do, and I'm sorry that I keep moving around these notes, but just so you can get a full view of different points, basically you send light rays through these totems, these glass spheres, and bend them according to the known geometry. And then you can get a NeRF reconstruction, and that's actually this over here, and compare that reconstructed view to the original unverified image to detect inconsistencies. And that's this heat map over here. So with the assumption that an adversary cannot make geometrically consistent manipulations, both in the image and in the four totems, the totems informally act as like private keys or sources of truth with their index of refraction and their private geometry. So this approach has a few limitations, one being the practical inconvenience of needing multiple totems for accurate 3D reconstructions, but most importantly, it requires a closed form model of how the physics of how the actual light rays get bent through the totem, which really restricts the approach to simple insecure shapes like spheres. So we introduce an entirely new framework for refraction-based image verification, where instead of requiring a closed form model of the physics, we instead learn a model of the refraction. And we do this entirely in simulation for now. So the way we do this is by actually synthesizing empirically generated training data. So this is sort of the setup that we're doing, and we can make a few approximations in simulation, like the scene is very far away, so we work with flat images. And the idea is to just scan a laser over the depth map of the scene, and for every sample point of the laser, we record the correspondence found in the totem. So we collect this pair of data, and just to recap, the totem basically is just some embedded image in this image I, and it's taking some transformation I prime. So we continue this over the full scene, many different sample points, and we build out a complete data set. This is the color correspondence. But this is a bit slow, especially for higher resolutions. And not only that, but in the real world, it's not really practical for a human to scan over the entire depth map of the entire scene with 100% coverage. We tested it out in the real world, and you can see here crosshairs which show basically the detected correspondences. So what we can do is sample at some reduced granularity, use an MLP to interpolate, and then when an unverified image comes in, like this one, we can basically run inference and get some reconstruction estimate based only on the pixels in the totem, using these mappings to do unwarping. Compare the two and detect inconsistencies. So here's an inconsistency heat map. Okay, so here are some initial results. This is the original image, manipulation, and here are our inconsistency heat maps following that method. This is an example comparing to an example from the prior works data set. So this was the original image, and we had to crop it to take out the four totems and insert our own. And we were able to synthesize our own results in simulation. And so we are also capable of getting these reconstructions, and especially a nice thing is that we avoid these NERF floater artifacts. This is our detection heat map. We pick up the color patch manipulation with pixel precise level. And just to quickly show, these are reconstruction results over the course of model training. So using frozen weights of the model and reconstructing at each point. Something interesting to note is in this area where there was no training data because the laser was obstructed by the totem, you can actually see that the model does a pretty good job of interpolating. So zooming back out to the idea that a totem is just some nonlinear lossy transformation of an image, and what if we considered perhaps more general, less smooth transformations? So a sphere is not really secure. Anyone can kind of figure out how to make a consistent manipulation in there. So remember, the key idea of our approach is that we enable independence of a closed form of the refraction. So that allows us to consider much more complex geometries. These are harder to model because of their very high frequency mapping functions, but we did get some promising initial results when we introduced positional encoding to the model. So we use sine and cosine frequencies, and it sort of allows the model to act as like a Fourier feature network with increased expressivity. So this is naively, this is with positional encoding. Here are some detection results. So here's a side-by-side of the sphere versus the knot reconstruction. We did test like 4 other shapes, but this is the upper ceiling of complexity. And while there's certainly future work that we're considering to improve the reconstruction quality, what we can say right now is this is the detection does work. It's just a bit less precise due to the reconstruction error. But so that's sort of where we're finding this trade-off with more secure but a bit less precise right now. And in summary, I'll quickly gloss over this, but we presented a new image verification pipeline embedding a physical signature, and that allows us to model complex optical behavior in a scene-agnostic way, which is a really important point because the previous work, you needed to re-optimize, do a slow per scene optimization for every new scene. In this case, our model is just coordinate specific and independent to the RGB coloring of the image. So in the future, we hope to incorporate more sensitivity and conditioning in the modeling on the depth, which is will be important, especially in the real world. But I'll end by quickly showing some initial results that we got in the real world over here. And yeah, I think that's everything. Thank you so much.
A little bit about how I believe that multimodal neural fields can be the missing ingredient to robot perception and planning at scale. And so in computational imaging, motivated by the mantis shrimp largely, I would argue, we explored modalities beyond RGB images, largely driven by what I would call interest-driven research or medical scientific imaging applications. And beyond HDR imaging and smartphone burst imaging, there have been a lot of niche applications coming out of computational. But I want to argue in this talk that the killer application is actually safe robotics. And I'll use autonomous trucking as an example during this talk. It's convenient for me because during my PhD, I founded a startup called Algolux that did end-to-end imaging and vision, and we merged with Torque and Daimler Trucks, and now we're building autonomous trucks, one of the Freightliner brand here in the US. So let me take this as a motivating example. So before I want to go into the meat of how multimodal neural fields can save robotics, let me start by going over the modern AV stack that we're developing at Torque, shown here at the top, separated into perception, prediction, and planning module. And learning is used at Torque in all steps here. This is, as mentioned, is a modular stack with parameters of all models being learnable, independently of that being neural network components or conventional algorithms that, if they're differentiable, we make them differentiable, or if they're not differentiable, then we come up with differentiable proxies and we train them in a network. So this allows us to treat the entire stack like one big giant neural network that we pass gradients through to the learned components or train parameters of these conventional algorithmic components that I just mentioned. And the fun thing is that You can see here on the representative drive on our pilot road with multi-camera, multi-lidar, multi-radar input, that this end-to-end training paradigm really works and actually informs the perception outputs of our multi-sensory fusion and learn prediction stack here in the early perception phase, which is quite a lot of fun. So using a modular stack has this benefit that we can train it in the end-to-end. This stack hinges on a long-range multimodal BEV feature processing module. On the right side, I'm showing you here the BEV perception output. So this is key so we can make long-range strategic planning decisions. And in the trucking use case, you have to solve a little bit more than what you have to solve for robotaxi applications because the ranges are so much longer. And you have vibration. So you actually have to tackle online calibration along with the extraction of features that you then bottle up to specific prediction outputs. The key thing that you need to learn or train this stack in an end-to-end fashion is data at scale. And you need directly the sensor inputs so we can perform end-to-end training. And this is where physically grounded neural fields can come into play and allow us to generate exactly that data, the physically grounded data that we need. So the goal of our world simulator that we want to train our truck in is that we want to create a large enough amount of physically grounded sensor data that we can use it to validate our virtual driver that we come up with. So we can use it both for training and validation. And the physical grounding makes it possible to allow for multimodal simulations that are consistent across sensors, that we can actually train multimodal sensing systems with, and that we can use from a safety perspective for both prediction and planning. So let's take a step back and look at how traditional training and validation stacks look at in the AV world. Here we have one real world that we deploy our trucks in. And then ultimately, during the capture, we're limited by the distribution of real world events and the number of real world trucks that we have. This traditional approach comes with two big disadvantages. First, we have to acquire these massive amounts of data first in order to then say, hey, look, we're going to throw certain ones out to finally only keep the interesting scenarios. So this is a resource war on the capture side. At the same time, we don't have any feedback loop with respect to the actions that are possible that are output by our virtual driver. So we can generate, using multimodal neural fields, data that is physically grounded and essentially turns one single captured scenario into a decomposed scene that then contains an infinite amount of virtual scenes, virtual worlds with retargeted actors and behaviors. And this then allows for closed loop training, where an action has an effect on other actors and our virtual sensor measurements, so we can really train our stack in a closed loop fashion. This core concept largely hinges on our work on scene graphs from 2 years ago out of my lab. So how does this work in more detail? So we recover a decomposed virtual world model using all of the recorded data from our truck that includes camera data, LiDAR data, radar data, and the IM. This model can then be rendered into sensor outputs, images, or LiDAR recordings, or radar recordings as well, which I will show you. So on a high level, use a radiance field-based scene representation for photorealistic images. And then we use an SDF-based model for the geometry. And we have a learned reflectance layer that sits on top of this SDF proxy geometry. And the fun thing is that if you design this overall system, you can design loss functions so that when the radiance sits on top of this proxy geometry, it can inform the proxy geometry and vice versa. So the images are finally then rendered given a camera pose and calibration parameters, and LiDAR point clouds are generated by ray tracing each laser beam using learned reflectivity. So here's the static scene extracted from a given drive. We recover the representation, the 3D representation decomposed into geometry and radiance automatically. This can be rendered into an image from the ego, or from arbitrary camera positions inside the scene bounds. And it's obviously obviously limited to the scene bounds only. So when we want to model the far range or background environment, we use an environment map that can also be used for relighting for this use case. We model all dynamic objects with individual learned 3D object representations. We can use Gaussian splats or other 3D radiance field-based representations to do that, as long as it's done together with pseudo-labeling and an effective approach. And this allows us then to simulate trajectories by accounting for the transformations over time and generate renderings of photorealistic images, LiDAR sensor measurements at arbitrary time. So the fun thing is that we can extract individual components of each scene and add them to our database and essentially build a database of 3D worlds and actor assets that we then can compose back into novel scenes. So for example, we can add the actors from our asset library to follow then a crash-based behavior and crash-based scenario that is consistent with multimodal sensor data, such as camera and LiDAR data. And you get also free ground truth labels from this decomposition, so you can even train the perception modules in isolation if you want. So let's look at camera data first. Here I'm showing you an original scene on the left side. And on the right side, I'm showing you a scene with an additional actor had a decomposed from another previous scene. And so we can get photorealistic renderings of our scene that can feed back into our camera branch of our modules. Here we have a scene where we're driving up to an intersection. You can see that the mounting position is higher than for some of the vehicles because we have a truck. And here you see the same scene with the ego vehicle following a highly wavy trajectory where we're simulating a bad control module that a planner needs to account for. Here's a scenario with a set of new actors. Let's just look at this scenario on the left side first, where we drive up to an intersection. And then we target this scenario and have a few actors that are repeatedly entering the scene. So this is good for litmus testing of our perception and planning stack. So now the interesting thing is that we want to simulate multimodal consistent data. Right? So here's a generation where we drive up to a ramp, where on the bottom you see the LiDAR radiance field simulated into the LiDAR point cloud, and then view consistent images on the top. Here I'm showing you now the same scene, but with a crash scenario. We drive up to that intersection, we have a vehicle in front of us that then rapidly brakes, so performs a hard brake, and we crash into this vehicle. These scenarios are very difficult to obtain in real world cases. You actually do not want to capture them and see them because it is a crash scenario. And so there's a huge value in multimodal radiance fields here. Here's another scene where we're just driving towards an overpass. And you can again see the nice pseudo labels that are coming out of our stack as a byproduct of the decomposition. And next, we retarget the scene here again as a crash scenario where we have a wrong way driver that is traveling in the incorrect line and ultimately crashing with our ego. Again, something that you don't really want to capture in the real world, but you have to make sure that your planner has seen it. And this, in fact, also all of the modules in the perception stack have to see it. Finally, is a scene with a pedestrian where not much is happening. We just are driving towards a pedestrian intersection. This pedestrian is walking across. So here's the same scene simulated, where the pedestrian initially occluded from the ego in the yellow bounding box here is rapidly approaching our vehicle and actually runs in front of the vehicle in the last second, and we would have to react to it. Let me play this once more, just so you see it. Here again, we have this intersection. So these are challenging scenarios that are essential for us to challenge both perception as well as planning models. And I already told you that you can directly decompose the scene into labels and data. So we can also train on this generated data. And we just want to do this for a perception module. And we can take real world data sets, take an off-the-shelf model such as a BV Fusion module and add our generated data to it. And evaluating on real-world captures, I can show you here results of training this off-the-shelf model, actually improves the performance in all cases. And from a different perspective, this is a clear validation of our simulation stack as is. Or unfortunately, we don't only drive in good weather. Here's an extreme snow scenario that we ultimately also want our stack to operate robustly in that we haven't captured at all. Point that I'm making is that these scenarios are rare. Here's a histogram of a 2 months capture through Europe in February. The data shows that even in February, these captures are heavily skewed towards good weather conditions. This also means that our natural data sets are all biased. So what do we observe here? Let's look at LiDAR. You can see on the bottom right, the problem with snowfall is that we get backscatter. Snowflakes produce unwanted noise in our LiDAR point clouds. And for comparison, you see the clear LiDAR point cloud on the left side. So can we simulate snow in radiance field with backscatter, turning clear data into snowing scenes? So let us look at the approach that we developed in order to do exactly that. So first we sample snowflakes on a 2D disk, as such. And then we do this not only once, but we do this for every channel in our LiDAR sensor. So let's say if you have a rotating LiDAR sensor with 64 channels, we do that 64 times. Then we stack them up and discard the snowflakes that are sampled outside the field of view. Then finally, for every channel of the LiDAR, we take one of such slices and we check for every transmitted ray, if and how much it interferes with the sampled snowflakes. And if you now look at one individual ray, indicated here on the top, we see that multiple snowflakes are overlapping with the beam because we have a diverging beam here. On the bottom, we see the received power over time or distance. And in this particular example, the orange snowflake here would cause the strongest return and kind of overshadows the measurements of the actual target that's at the far end of the range in black here. And we simulate the final return with a DSP measurement in the loop now that actually outputs the first return, which will be the orange measurement. And on the bottom here, let me just restart my slides because they won't play. Okay.
Okay, we're allowed up to 2 more like Zoom problems and then
Okay.
we're at quota.
Then we're at quota. Okay, perfect. On the bottom, we see results of the snowfall simulation for clear weather scenes. On the left side, you can see that our method mimics real-world LiDAR according to snowfall shown here on the right side. So qualitatively, this works. And see this also for 3D object detection as a simple downstream task. In the first example shown here in the top row, we can see that it's able to detect the pedestrian and snowfall clutter in front of the ego vehicle. So got another example here, the second example, the only method comparing to traditional augmentation method that does not predict any false positives. And the third example here showing that we're the only method detecting the lead vehicle that's whirling up some snow and causing clutter that other methods cannot remove. So this is an exciting method that shows us that we can use these radiance field representations for harsh adverse conditions as well. So we talked about LiDAR so far. We know cameras and LiDAR are complementary. So what about time-gated hybrid sensors between LiDAR and camera that do better at each task than both together? This is another key sensing methodology that ultimately is largely exploiting computational imaging, but has really high potential for robotics. So why is that? Well, today, if you look at 3D perception in autonomous vehicles, this largely relies on LiDAR and a lot of fully level 4 AV stacks. Here's an example of a Velodyne Alpha Prime. In contrast, RGB images from CMOS sensors have really dense, high megapixel outputs, but are lacking depth precision. Gated imaging is a methodology that is kind of a hybrid of both, that has the spatial density of an imaging array, but has some sparse depth information because it has an active illumination source. So how does this work? So what's gated imaging? So use a floodlight illuminating a scene where the reflected laser pulses are then captured by a synchronized gated exposure on the camera. This is a nanosecond camera shutter that exposes only the photons that come back from a range of roughly over 30 meters in range distance. So you see the pedestrians illuminated high, but there's some spatial overlap of the laser scenes. And by varying the delay between the laser pulse and the gate, we can illuminate different parts of the scene at different depths. So here I'm capturing the vehicles further in the scene, and finally the traffic lights all the way in the background of the scene. So we get some coarse depth information that's kind of overlapping and encoded in the relative intensity of these gated slices. And the fun thing is that we can learn a radiance field or use radiance field-based methods to extract scene geometry and scene detail at high resolution. So how do we do that? We learn a radiance field from the gated images with 3 temporal slices. So in order to do that, we cast rays. So let's say these are our temporal slices here. So we cast rays from the camera into the scene and then trace back to the source. Because we ultimately illuminate the scene from the source, we need to get back to the camera and then modulate this response over time with the calibrated range response function. And in this process, we take both the spatial profile and the pulse profile of the temporal gating into account. So such as the scene shown here allows us to capture accurate geometry from a single drive through a scene with this novel gated camera very effectively. So the way that our neural representation works in detail is as such. We start with a hashgrade-based encoding that is indexing into a single joint density field that encodes the density of the scene here. We then decompose the scene into a normal field, a learned ambient field, and an appearance field, and a shadow component that is coming from ray casting through the density field. The ambient, normal, and shadow field are then used to model along with the scene reflection the final observation. And so as mentioned before, the illumination profile and range intensity profile are then directly used in the rendering as well. And here's a rendering equation with these individual components. So along a ray, we accumulate intensity of the light source, and then the active components based on a normal weighted reflectance and accumulated light intensity are shown here in the top, where we combine the active component, the range weighted by the range intensity profile with a normal due to the foreshadowing. And with this decomposed radiance field, we can then not only generate novel views, as shown here, high fidelity and depth, but we can also do a bunch of really fun things, such as change the location of the illumination source with accurate shadow casting in the scene. Here I'm moving this illuminator on the car from before, back and forth. You can reduce the ambient light in the scene to simulate challenging capturing conditions, or increase the laser power for a gated simulation, allowing us to simulate other new gated scenarios that we must handle in our robotics stack. So from gating, we're then able to recover high spatial resolution depth information that actually outperforms existing RGB or RGB plus LiDAR or LiDAR only radiance field-based methods that folks have been producing in the past. And the bottom shows you here depth renderings for a daylight scene. So because of the active illumination, we get high quality reconstructions in harsh scenes at night, in rain or in snow, which is shown here at the bottom. And we get accurate reconstructions of the normals that are also directly recovered as a byproduct in nighttime scenes from the model with high accuracy. And this neural representation is directly integratable into the previous camera LiDAR model, the multimodal model that I mentioned before that we use to simulate our entire training data for our end-to-end models. Okay, so having reviewed camera, LiDAR, and hybrid gated sensors as potential big benefits of sensing stacks that we can combine together in neural fields, I want to last describe how we can also use a radar and support this in a neural world simulator from before. And this builds on our radar fields work, which is introduced at SIGA. So let's consider a 2D FMCW radar, the cheapest radar that you can imagine. FMCW radar sensors send out hundreds of beams in all directions and collect waveforms from the reflections here in blue. This gives us a frame with these waveforms and conventionally would apply some form of a peak finding algorithm that's implemented on the DSP and then get these very sparse points here that are prone to clutter, shown in red. So this is essentially the input to a lot of downstream tags that are being used. So when we do this, we're losing a lot of rich information that's in the original waveforms. So can we use the waveforms themselves? With radar fields, we're able to take these 2D radar measurements and accurately reconstruct a dense, detailed 3D geometry, not just a 2D one, but a 3D one, of a single drive-by scene. So you see exactly such a reconstruction of the scene. So how does this work? Well, we supervise radar fields with raw frequency modulated wave radar data. So these sensors emit chirps, so it's a linearly modulated frequency signal. And here after emission, let's just assume that the beam diverges, hits two scene objects, and the reflections come back to the sensor. Then due to the travel time, we get a phase difference between the transmitted wave and the reflections. And with frequency modulation, a phase difference also means a constant frequency difference. So if we correlate the reflections with the original waveform and look at it in frequency space, we see these peaks here corresponding to the distances where there were reflections. And this is a raw frequency space waveform that we're supervising our model with. So how do we predict what received power we have in the respective frequency bins? So for a given frequency bin in the FFT, that's the power PR here, we can define it as the amplitude proportional to the transmitted power and the antenna gain. And this is divided by the distance from the sensor squared because of the inverse square law. And then the last component, that's the radar cross-section. And this is an entangled entity that depends on the object transparency, geometry, and material parameters. We will learn that with our neural field. We factorize it into three individual components that we learn: occupancy, reflectance, and directivity. And we then insert this into our forward model. So how do we learn? This here is our radar fields forward model. This is our radar fields neural model, where we query the 3D space again with a hash grid, just as before. Embed this with an MLP. We get XYZ features that we feed into two neural components, one for occupancy, one for reflectance. The reflectance component also gets this additional directivity component that we encode with spherical harmonics. Then the two predicted components of our radar cross-section are passed through our forward model that I mentioned before, that you just saw. And then we can supervise this with the raw radar measurements and use an L1 loss here in this case. So how do we get 3D out of this? Well, we need to integrate our beam integration. So in order to learn the 3D representation, we take for each beam the center, consider a cone around it, and then defined by the divergence of that particular beam, then we sample within this cone and integrate all of the individual samples within this cone, both along azimuth and elevation, to get a single predicted waveforms according to the profile. And then from this antenna gain profile, surprisingly, we get actually all of this 3D information. So just from the radar drive here, you can get many of these structural elements, these bollards, other signs and elements just from the radar measurement. Here's one more side-by-side scene. The scene is a little bit longer. And then finally, let's look at adverse weather, which I motivated before. So here's a camera data measurement from a foggy scene sequence in our data set. And we try to reconstruct this with a nerve-based method or a Gaussian splatting-based method. We don't take into account scattering. With the longer wavelengths that we get from a 2D radar sensor and really cheap sensor, doing a side-by-side comparison, you get pretty decent measurements out here where we can see the signs, bollards, light poles. Again, all of this with 2D information. So hopefully, with all of these different modalities, I've convinced you that physically grounded multimodal neural fields can be the missing ingredient to robot perception and planning at scale. So this really can be the killer application for a lot of work that we have been doing in computational imaging. This allows us to generate physically grounded counterfactual scenarios. In some of the other workshops, I'm talking about the behavior simulations that are key and can build on top of this, which is exciting. Allows us to train, validate, and challenge modern AV stacks and robotic stacks. especially with scenarios that you don't want to see in real world, such as this crash zone. Building ultimately towards superhuman safety in robotics. Thank you.
Thanks so much. I think we have time for.
Okay, great. So I'm going to just set the stage for the off chance that someone wandered into the room without knowing what neural fields are. And so the stage is around 2019, 2020, neural fields started to become really popular. In this community, it was through NERFs mostly. But in the fluid dynamical community, people started looking into neural fields to solve fluid dynamical equations. Now, at that time, I started my postdoc at Caltech, and I've started working on imaging fluid dynamical phenomena. And so both of these kind of aligned really nicely with my work and shaped the work that I've been doing since. And so the scene was NERF came out, and it kind of had these two different ingredients, right? It has the representation, which is a coordinate-based neural network, and it has this other part, which is a differentiable volume rendering. And naturally, in the vision and graphics community, everybody focused on this part that's called the representation, which is how do we get a better representation? How do we get a faster one? How do we represent larger scenes, more intricate scenes, and so on? But what I found when working on astrophysics or scientific imaging problems is that's not the bottleneck. The representation is important, but really what was important is this other part, this volume rendering, right? And to generalize it to more complex volumetric rendering or more complex radiative transfer. Okay, so the talk today is really one about scale. So I alluded to that when I said the entire scale of the cosmos. And I really like this video. This is a video from the 70s, so bear with me with the blurry resolution. But this video starts with this couple having a picnic. So basically, I don't know if you guys can hear it, but there's a couple here. It starts at 1 meter wide, and every second we're going to zoom out by an order of magnitude. Okay, so we go to 10 meters and so on. Now this video continues, and the key thing is that a typical NERF scale is on this scale, the scale of the picnic. Sure, some might be smaller, it could be a tractor. Some might be larger, it could be a whole cathedral, but that's the scale of meters. Now, I want to zoom out well past the scale of the continent and well past the scale of the planet until we can't see the planet anymore. And now we're seeing the orbit of Earth, and then we're seeing the orbit of the rocky planets and the gas giants, and now we see the entire solar system. Okay, so this is the scale, 10 million meters. Sometimes you can already transition to light days here, but you can still keep this in meters. So what's interesting in the scale of the solar system? Well, we were working on this problem and we wanted to figure out, one thing that astronomers are interested in is figuring out the physics of how the solar system was formed, right? And unlike archaeology or geology, you can't just go and dig things up or carbon date things, right? But luckily in astronomy, you can look at other instances. You can look out to the distance and you're going to see young solar system in their infancy, okay? Or as they're known as protoplanetary disks. Okay, so we wanted to reverse time, right? And take the solar system back to its infancy, to a stage where mainly what we see is this bright spot in the middle, that's the star, and then a whole bunch of gas just swirling around, okay? No planets just yet. Okay, so that's the state of a protoplanetary disk. And so the goal here was to image these protoplanetary disks. And if you look at, and we're imaging them with this instrument called the Atacama Large Millimeter Array in Chile. And if you look at the right at the survey of ALMA, what you see is that they have this really intricate structures. They come in all these different shapes and sizes. And these modes, they highlight the fact that behind these images, there could be really interesting physics at play. Okay. And so the different physics will push the system into different states and will reveal different image features. And so what we want to be able to do is actually model these disks as neural protoplanetary disks. Okay. And so this is joint work with all these great collaborators. Okay, so let me separate this a little bit from the standard NERF RGB camera scene. So in the standard scenes, what we have is this really kind of broadband emission. Okay, so what we're seeing is not really emitting at every single frequency, and our sensors don't really measure single frequencies. They have this kind of broad spectral response. And the difference here is that we're looking at a molecular cloud, and molecular clouds emit at a very, very, very narrow frequency range. So for example, CO emits at 230 gigahertz, and that's exactly the frequency that ALMA is centered around. Now, this is not coincidental. This is because ALMA was designed to see CO, right? Because it's one of the most abundant molecules in the universe. Okay, and so when you're looking at molecular clouds of gas, you're no longer looking at broadband emission, you're looking at line emission. Okay, so in fact, ALMA can even give us really fine resolution in frequency. So imagine taking this range that ALMA can see, and imagine splitting it into really fine bins in frequency. So if you use the the NERF standard model to model this, what you'd see is I've got an empty image, empty image, empty image, and then exactly at that delta frequency of CO, I can see the disk, and all of a sudden I'm seeing empty images again, right? That's what you expect to see. But that's not what ALMA sees, okay? So ALMA sees this really interesting structure in frequency. So where does this structure come from? It comes from the fact that the disk is not stationary, okay? So in fact, what happens is the disk is moving. It's orbiting the central star, and what's moving towards us is being blue shifted or Doppler shifted, and what's moving away from us is being red shifted, okay? So it's shifting the emission in frequency space. It's shifting this central line of CO either to higher frequencies or lower frequency, depending on the motion. And so the spectral data cube that ALMA can capture gives us some information about velocities, right? So not just emission, also velocities. Okay, so another interesting thing that we can see here, we can see this structure that looks like butterfly wings, like two distinct layers being separated, right? We can see this in the data cube. And the question is, where does that come from? So a typical way that people model these disks is they have this CO layer, and it's dictated by the overall temperature around it. And at some point, close to the midplane, there would be freezing. The CO would freeze into ice and no longer emitting in radio wavelength, okay? And so that's what's causing this separation of the two layers. And so it looks something like this. You have this disk model, and you say that it's mirror symmetric, and you say that it's also azimuthal symmetric, and you have some velocity there, right? And so this gives us the structure of every image. It looks kind of like two butterfly wings. And also, because of Doppler shifting, you're going to get this structure in the frequency space. Okay, so that's kind of the basic modeling of how people look at these disks. And what do they do with this? So now they take this CO layer model, and they say, well, we're going to parameterize it with maybe 8, 9, or 10 parameters, and we're going to recover them. We're going to search over them using some sampling MCMC approach, and we're going to find the best parameters that fit the data that I have from ALMA. And what we said is, what if we replace this with a neural field? Okay, so this is what I mean when I say physics constrained. I don't mean the radiative transfer physics. I don't mean the ray tracing. I mean that this neural field doesn't represent anything to do with radiances. It's temperatures. And the way that we relate temperatures to radiances is through some physical laws. For example, if this is an equilibrium gas, and we can use the ideal gas law, we can translate temperatures to densities, and we can translate densities to emissivities, okay? And so there's some physics in the background that takes in this neural field and translates it to emissivities of CO, and that's what ALMA can see, okay? Okay, so let's look at what we can get from that. So here's a case study. We're looking at this disk. This is actual ALMA observations, and these are a couple of slices in frequency. And what we see is that if you use this parametric model approach that people are using in the astronomy community, what you get is you get it doesn't matter how long you scan for the best fit parameters, you can never represent some of the data features. For example, the layers where the arrows are, they just seem too separated. They look kind of like a staircasing. And the parametric model just can't capture the physics that's actually happening and the structure that's existing in the data. Now, of course, the neural field is more flexible. And so all of a sudden we get a much better data fit, right? So all of a sudden we get this smooth transition between the two layers, and we get something that represents the data a little bit more faithfully. Okay, so okay, great. So we represent the data, we can fit the data better, but what can we learn from that? Well, let's look at the temperature profiles that we recover, right? So on the top, we have the best fit parametric model. And on the bottom, we see this really complex CO layer that we recover, okay? So a few things to know here. On the bottom part, you can see all this CO junk, all these isolated islands of CO. Can we trust those? Well, the answer is probably not, right? Why can't we trust those? Because this is the bottom of the disk, and photons, and this is an optically thick disk, so likely photons that come from the bottom don't even make it past the disk, okay? So this is not really well constrained by the data. But what we can trust is that we see that to represent the data well, we need a disk that transitions from thick to thin. And this is something that the parametric model, no matter how you spin around these 9 parameters, cannot come up with, okay? And so the key is that the flexibility of the neural fields lets us come up with a new physical parameterization that maybe can hint at some physics that we don't understand well, okay? Okay, so I'm going back to this scale diagram. Remember, we were at the scale of the solar system, and I'm going to start zooming out. So I'm going to try and cover maybe three more works in this space. So if we start zooming out past the solar system, we're going to transition into light year scales, and we're going to zoom well out into the 100,000 light year scale, where we can see the entirety of the galaxy. Okay, so this is the galactic scale. Now, right here at the very center of the galaxy lies a supermassive black hole called Sagittarius A star. And this is the first image of Sag A star that we took with the Event Horizon Telescope. Now, why does this image look the way that it does, and why do we think it's a black hole? Well, the reason is that general relativity predicts that if you have something that's very, very massive, light doesn't move along straight paths anymore next to that object. It's going to curve space-time in such a way that light that comes from behind the black hole won't be occluded, but it will actually be gravitationally lensed. This is called, the black hole acts as a sort of lens onto the image, right? And create this ring-like shape, okay? So it's this ring-like shape. It's the darkness in the middle of all this brightness that is the smoking gun that Sagittarius A star is indeed a black hole. Okay. Now there's a lot to say about this image, but that's a topic for a different talk, and so I won't go into this, but you can catch me on the break if you want to talk more about this image of Sag A star. But the question we were interested in is, can we move past a two-dimensional image and get a 3D reconstruction of the emission around the galactic center black hole? Okay, that was the question that was interesting to us. And can we do it using neural fields? And so here, this is a reconstruction. And I want to ask the following question. What is it that we're actually seeing here? Okay, so what we're seeing here is an event occurred on April 11 of 2017, and we collected observation right after this event. This event was called a flare, and we suspect that the physics is not too dissimilar to what's happening around in the sun when solar flares emerge, okay? The only problem is this is happening 25,000 light years away from us. So not in the galactic scale, not in the solar system scale, but in the galactic scale, okay? And using neural fields, we were able to reveal what this structure might look like, okay? Now, usually this is the part of the talk when I start highlighting all the technical challenges that were involved and how we were able to reconstruct this three-dimensional thing using general relativistic ray tracing and throw a lot of technical terms into the air. But I want to focus on some higher level concepts right now. The first concept is, And this is mostly geared towards students that are interested in working on this kind of regime of neural fields, well beyond conventional cameras. Okay. So the first high-level concept is the data is super important and very specific. Okay, the data is more important than the method in this regime that we're working on. This is really exciting data that we coincidentally were able to capture right after an interesting event happened. So now we have a lot of time working to understand the specificity of the data acquired on April 11, 2017 at 8 a.m. Pacific time, right? So we are really focused in on the specific data set. And it doesn't matter if you develop a new method if it doesn't refactor this data to highlight something interesting about it, okay? And so it's not about the method, it's about the reorganization of the data and what it can reveal to us. The other point that I want to make is we tend to think of neural fields constrained by some physics, let's say the rendering equation or some other radiative transfer equation and so on. And we tend to think of the physics as being certain, okay? And in this regime, the physics are highly uncertain. They're actually state-of-the-art, they're a combination of state-of-the-art different observations and simulations that we needed in order to constrain the physics in this reconstruction. And so a lot of the work goes into exploring all of the systematic biases and uncertainties that we are putting into the system by plugging in physics that we are not entirely certain about, okay? So this is a big part of the work here. Okay, so now some black holes are not as dormant as Sag star, and they emit these galactic scale jets, okay? These jets span out the entire length of the galaxy. So on the top left, it's even a couple orders of magnitude larger than the galaxy that's just a single bright pixel in the center, Cygnus A star. Right, so these black holes are very different to the one in the center of our galaxy, that it's relatively tamed, okay? And in the previous work where I showed the 3D reconstruction, this wasn't actually a reconstruction of something that's in the scale of the galaxy. It was a reconstruction of something that's more on the scale of the solar system and embedded in the center of the galaxy. Right? Now I'm going to show you a reconstruction of something that is as large as the entire galaxy. Okay, so this is really cool work. This is work to do a dynamic reconstruction of one of these jets. Okay, this is 3C345, and what you can notice at the top there is that the observation period spans from 1995 to 2022. Okay, so almost 30 years of observations. And this is what's called multi-epoch observations. So every year astronomers point the instrument to the same little bright pixel in the sky and acquire observations. Now we can take all of these observations using a dynamic nerf, a nerf that takes in space and time, and reconstruct this entire video sequence. And on the bottom, you can see that we can also reconstruct the linear polarization and get an optical flow estimate of what's happening in this jet. And so just to put this in perspective, this is the standard method of reconstruction used in radio interferometry. It's called clean. And now you can really appreciate all of the features that you can reconstruct if you use a neural field as compared to the standard VLBI approach. And VLBI is very large base interferometry. Okay, so that's great. Now I just want to highlight that this is, I want to highlight my collaborators and especially the students working on this project and doing all the heavy lifting. So it was mostly work done by Mariana, Antonia, and Brandon. And this is work that's under review in Nature, but I think the general theme here is that I want to separate it from the traditional camera and NERF. The general thing that I want to highlight is this is observations over 20 years. So when we go out and we acquire some multi-view observations from NERF, maybe you acquire the same observations with the same camera in the same day. Maybe you do it over a couple of days. Maybe you even do it over a month. But here we're talking about observations over 30 years, okay? And that's where a neural representation really comes in handy. You don't have to grid this entire thing over 30 years, right? You can just have a continuous representation and you can parse observations that are multi-epoch, meaning in every epoch you could have maybe a couple of days apart of observations, and then there's a huge gap, and now there's a year of a gap, and now you have more couple of days apart of observations. Okay. So the last part is really the cosmic scale. And I kept Brandon here on the screen because that's his work that I'm going to be highlighting. So if you really zoom out, well past our own galaxy, zoom out to the scale where each galaxy is just a single point light source. Okay, galaxies are just point light source in this scale. You're going to start seeing interesting effects. And so the effect that we're after is gravitational lensing, right? And again, as I said, gravitational lensing really treats mass as a sort of lens, okay? And it causes a curvature in space and time that makes light rays move along curved trajectories. And if you're looking at gravitational lensing, not of a black hole, but of something much more diffuse and much less massive, then now you're starting to a first order approximation, you can actually approximate this as just refraction. And so we saw a couple of talks and posters about refraction. And in fact, you can recover a refractive field in the scale of the cosmos. And this refractive field will give you an indication of where dark matter lies. Okay, so that's a really cool line of work. And so again, we utilize neural refractive fields, and these refractive fields are actually an indication of mass, and most of the mass that we see between us and all of the galaxies millions of light years away is actually dark matter. Okay, and so that lets us use neural fields to probe the large-scale structure of the universe, which is, I think is something that's super exciting, and this is ongoing work. Okay, so this is work led by Brandon, and again, the little clip that I showed is a very exaggerated clip. That wasn't very realistic refraction from dark matter. In fact, the curvature that's caused, the gravitational lensing that's caused by dark matter is very, very tiny. It's actually called weak gravitational lensing, and it's sometimes could be on the order of sub-pixel shifts, okay? And so the signal is very, very weak. And you can model this signal not just as refraction, you can also look at what happens to the ellipticities of all these galaxies. And so if you see correlations in the ellipticities of all these galaxies where they shouldn't be, right, because all these galaxies were created separately in very large distances, then you attribute all these correlations to what's between you and the galaxies, and that's dark matter. But how do we get three-dimensional structure in this case, right? We only have one viewpoint. Well, the key is that in astronomy, the redder the object is, the further away it is from you. Okay, and that's to do with the expansion of the universe. And so if you also have the spectrum of these galaxies, you can estimate your distance to them. And that gives you some three-dimensional information. Okay, how am I on time? 2 minutes, okay, good. Okay, so this is actually my last slide, and I want to finish up with just a thought. And so I showed you how neural fields actually work on these extremely large scales of reconstruction, right? And very different scales, orders of magnitude, from our own solar system to the galaxy to the entire cosmos, and they work really well. And it's not surprising. Okay, it's not surprising that neural fields work really well in all of these different scales, because all of the phenomena that I was looking at is fluid dynamical turbulent phenomena. Right? And the one thing that is, and this is what's in common to all of these phenomena, is that they're turbulent, and turbulent has energy in all scales. And so if you keep zooming into a turbulent field, you're still going to see the self-similarity properties. It's still going to continue to look the same. And so I could have actually renamed this talk and talked about neural turbulence field. That was also a possibility to name this talk. But turbulence is a way more broader topic than just astronomy. Okay, so turbulence is our atmosphere. There's turbulence in the blood in our veins that dictates how medicine is going to be delivered to our cells. There's turbulence in just about every scale that you can think about. Okay, and so my one final thought is if neural fields are really good for turbulence, then there's a whole host of other applications out there that we can explore. And with that, I can take questions.
If there's any questions, where is there? Oh, question in the back.
Okay, it's more important, okay. Yes, okay, so this talk is gonna be let me first say who I am. Hi, I'm Sarah Friedovich-Kyle. I'm a new assistant professor at Georgia Tech. This work is gonna be a mixture of work that I did during my postdoc at Stanford, hence the Stanford logo, and some work at Georgia Tech, hence the Georgia Tech logo. I wanna just highlight my collaborators on this, especially the two students who really did most of the work. So Irmak is a PhD student at Stanford and Namhoon is a PhD student at Georgia Tech. Okay, so this talk is going to be more foundational about the structure of INRs, or the structure of how we represent signals for the context of inverse problems. Okay, the first sort of piece of this is going to be introducing a specific volume representation called geometric algebra planes, because it's inspired by primitives from geometric algebra. And I'll give a few reasons why this is a good representation and favorable properties that it has. And then I'll take a step back and just benchmark where we're at with implicit neural representations. Yeah, question? Oh no, excellent point.
You can just click more and then hide the two things.
Beautiful. Okay, thank you. Okay, the second part, we're going to take a step back away from this specific representation and just try to benchmark where we're at with volume representations in general, compared to a very simple baseline that turns out to be stronger than we expected. Okay, so to dive in on this, geometric algebra planes, a lot of the motivation for this was just compression. We wanted to have a memory efficient representation for radiance fields, but also for other inverse problems. But here I'll show radiance fields. Okay, so GA planes, I've been describing this as a model, but it's actually a whole family of models. So how do you pick a model from this class? So first is you choose a set of geometric primitives and represent them as feature grids. So fundamentally, this is a hybrid model. It's going to have some parameters in grids and then some neural network decoder. So the primitives that you have to choose from in 3D would be line features. So this has some 1D resolution R and then a feature dimension D. You can also have plane features with 2 spatial resolutions and a feature dimension. And you can have a volume grid with 3 spatial dimensions and a feature dimension. And we're going to allow you to use any of these, any combination of these. And then we're going to in order to evaluate what's happening at a specific point, Q, we're going to just project Q into each of these, whatever grids we've chosen in our representation. We'll interpolate in those grids, and that'll be our feature that we'll extract out. And then we're going to choose some operations to combine these primitives from these different feature grids along their feature dimensions to get a combined feature. So we'll allow addition, concatenation, and element-wise multiplication. And then lastly, we'll choose some kind of decoder that's going to map these features into whatever outputs we want. So this might be density, color, etc. And we're going to consider 3 different types of decoders. There's the classic MLP decoder, and then we'll also consider a convex MLP or just a linear map, just to get a sense of how these different choices of feature grids and decoders affect the representation capacity of what we're able to get. Okay, so the specific model that we're going to use for radiance fields, this non-convex model, looks like this. In this notation, here's a picture version. So we're going to have line features, which we call E1, E2, and E3, and we'll multiply them together to get a volume. We'll also have plane features, E2, 3, E1, 3, etc., which we'll multiply with our line features, again, to get a volume. And then we'll have a single volume feature. And we're going to combine all of these different sort of ways of making a volume by concatenation. But you could also do addition. Okay, and then we'll decode the whole thing with an MLP. There it is. And just why not? We'll have multi-resolution copies of all of this. So all of our features can capture content at different scales. Okay, so I've described this as a very broad sort of family of models. I want to just really drive home that point by showing that a lot of other classic implicit representations can be couched in the same language as a member of this GA-planes family. So the one that I just described is at the top. We also give a convex or semi-convex formulation of this that I'll talk about later, which is a little bit simpler. Basically, it just doesn't allow multiplication. So everything is concatenated instead of multiplied. But you can also think of vanilla NERF in this category. It's just a decoder with no feature grids. At the other end of the spectrum, you can have a volume-only model that just has E1, 2, 3, and maybe a decoder. Same thing with tensor F, triplanes, K-planes, MERF. I could go on, but these are just different ways of combining some kind of grid feature with some kind of decoder. Some of these I'll just highlight sort of obey properties from geometric algebra that inspired this particular work, meaning that whenever you multiply two grid features together, it has to sort of represent a volume at the end of the day. But anyway, that's just an aside. Okay, so why do we do this? How does it work? So this is just showing on the y-axis is PSNR, on the x-axis is model size on a log scale. Our goal here was to get compression. So we want to represent a scene as faithfully as possible with as few parameters as possible. This is just the classic like NERF Blender data set showing a bunch of different models that allow us to vary their size, and we can evaluate how well they do. So this dark purple line on the top is GA-planes, the full model, and then all of these other curves are either ablations of GA-planes with some subset of the parameters, but not everything, or other classic models like TensorF, K-planes, MIP, NERF, so on. The same trends basically hold on different metrics, but the point here is that this particular parameterization that I presented 2 slides ago allows us to get sort of the most graceful decline in performance as we shrink model size. Just to show a few pictures of this. So this is K-planes on the left and GA-planes on the right, where we tried to match the model sizes, but the GA-planes model is actually smaller here. Hopefully you can tell there's more detail. I'm not sure how visible this is. I think this one will be very visible. Okay, so just to show you, you do get more detail with the same number of parameters with this parameterization. Okay, the takeaway that I want you to get from this first section of this talk is that this particular non-convex GA-planes model, at least of the ones we compared, it's Pareto optimal on model size and representation quality for this radiance fields task. Okay, so I mentioned at the beginning that we have also a convex version of this GA-planes model. I want to take a brief detour and just explain what I mean by that and why we should care about it, since the model I just presented was non-convex. Okay, so firstly, why do we care about convexity? So for one thing, there are a bunch of different optimization algorithms and specialized solvers that are designed for convex optimization and are very efficient at convex optimization, above and beyond what you would expect from like a first order method that we use on most non-convex problems. These can also often come with built-in sort of optimal hyperparameters, so there's less tuning to do. They also come with guarantees of convergence to global optimality. You don't have to play with initialization, and you won't get stuck in a bad local minimum. Okay, so everything we've talked about so far is non-convex. So if convex is good, how do we get it? Well, so for one thing, we need to use a convex loss function. So mean squared error is pretty common. It's convex, so we're good to go there. We also need to restrict ourselves to inverse problems that have, here we're going to focus on linear forward models, but more generally anything that will make the final loss function convex. So lots of problems solved in this category. Radiance fields unfortunately doesn't, but CT, MRI, pure compression or super resolution, in painting, all these things are linear. And in this GA-planes model family, we have to restrict ourselves to linear feature combinations. So basically no multiplication of features, but we're allowed to concatenate and we're allowed to add.
Okay, so this is the model that we're going to use for convex experiments. It's just taking all of the possible feature grids we're allowed to have and concatenating them. And we're also going to replace this standard MLP decoder D with a convex MLP decoder. I don't think I have time to explain what those are, but if people want to ask me afterwards, I'm happy to talk about that. Okay, so probably should have made this bigger, but just to give an experiment showing that these convex GA planes actually do bias something. So this is a particular, we're fitting a video segmentation mask here. So it's a convex problem. And we did this with 3 different versions of the GA planes model, the convex one, which is blue, a semi-convex one, which is in between. It's still guaranteed to converge, but it's not quite as well conditioned perhaps as the convex one, that's in orange. And then a standard non-convex model, which is in green. This is a very small model where it's pretty sensitive to initialization when it's non-convex. So the green model, just repeating over different seeds, you get wildly different performance. Sometimes it converges, sometimes it gets stuck. Whereas the convex and the semi-convex models, they basically work regardless of initialization. So as we try to push towards more and more compressed models, having convexity allows us to still converge in a loss landscape that otherwise would have been hard to get through with a non-convex model. Okay, so takeaways from this brief detour is just to show if you're working with a linear inverse problem, there are benefits to using a convex representation, and that GA planes is one such representation that works well on these problems. Okay, so one other piece that I want to give about GA planes is that we have some associated theory for the sort of subset of GA planes restricted to 2D. So everything we've talked about so far is in 3D, but we can imagine the same model in 2D where you just throw away the 3D component. And in this 2D subset of GA planes, there's some really interesting connections to matrix completion that help us understand what the capacity of this model is. So I'm not going to give you the full theorem statements, but I want to give, which are in the paper, I'll link at the end. But I want to give the main sort of punchline, which is comparing different ways of combining features on the left, and on the top, different decoders. And for every combination of how we combine features and how we decode features, we can analyze what's the maximum attainable rank of this representation in the matrix sense, right? It's a 2D representation, it's representing a matrix, we can analyze what maximum rank it can represent. If you have a linear decoder, the best you can do is multiply features, and then you're going to be limited by the feature dimension, which here I'm calling K. Sorry, I called it D before. But this is the feature dimension. It's just analogous to rank, like in SVD. But as soon as you go to an MLP decoder, whether it's convex or non-convex, the rank restriction here, instead of being based on the feature dimension, suddenly we're not bottlenecked by that anymore. Now the rank is limited by the resolution of the features. So these E1 and E2 are literally vector features with resolution R1, and that becomes the maximum rank. So the adding of an MLP decoder, whether it's convex or non-convex, can dramatically improve the representation capacity of this model. Just to show what this looks like, this is a kind of simple example where we're just trying to fit an image with one of these 2D models, comparing all of the versions in this grid. So solid lines here are multiplying features, dotted lines are adding features, and then you can see different types of decoders in different colors. As you'd expect from the table, the MLP decoder with multiplication of features is doing the best. You can tell pretty clearly with the linear decoder in green that there's a huge difference between multiplication versus addition, as we expected from the theory. And moreover, we added this black line here is just the SVDs. This is the optimal rank K approximation of this image. And just by adding this MLP decoder with the same number of parameters, we're able to beat that optimal decomposition. So we are doing better in terms of rank than the SVD. Okay, so that was actually a not even the full GA planes model. This is only the line features. You can also have a plane feature if you want to do 2D GA planes. And in that case, GA planes ends up being low rank plus low resolution. So the 2D grid is the sort of a low resolution component. And we just compared, again, for fitting a simple image. In green here is this low rank plus low resolution approximation, whereas in blue is just a classic low rank plus sparse approximation from signal processing, and just showing that this low rank plus low resolution is doing better in terms of compression. Okay, so takeaways from this part of the talk. In 2D, we have this equivalence between GA planes and a low rank plus low resolution matrix completion model. The choice of how we combine features and how we decode features can dramatically affect the rank or expressiveness of the final representation. And in this case of fitting a natural image, this low rank plus low resolution decomposition works better. It is more faithful to the original image compared to low rank plus sparse for the same number of parameters. Okay, so with that, I want to transition. Now we've been talking about the specific GA planes model for a while. I want to switch to a broader view where we're going to just try to benchmark what is the bandwidth of an implicit representation. I think this is an interesting fundamental question that we're going to just set up a benchmark for. Okay, so how would you try to measure the bandwidth of an implicit representation? One way to do this that we cooked up is to just come up with synthetic signals where you can control the bandwidth of the signal, and then fit these signals with a bunch of different representations where you can control the size of the representation. And this will give us some sense of how each model is allocating its representation capacity among these different band limits. So we have these three synthetic signals. I'm showing them in 2D. We actually did them in both 2D and 3D. So the bottom one is like truly band limited. We took noise, we filtered it in the frequency domain. The top two are sort of intuitively capturing a notion of band limit in the sense that the feature scale gets smaller as the bandwidth goes up, but they're not, they're trying to capture some features that we might see in natural signals like sharp edges. Okay, so each of these signals has inherent dimension 10 to the 6, so it's like 1,000 by 1,000 image or 100 by 100 by 100 volume. And we're going to fit them with models where we're going to constrain the model size to be at the smallest 10 to the 4, so like 1% of the signal size, up to 3 times 10 to the 6. So we're going to allow it to go a little bit over parameterized, just to test both compression and sort of stability as you become over parameterized. Okay, I'm not going to show all the results from this. The paper is going to be out on arXiv tonight, but I'll give those sort of highlights. So this is those three signals that I just showed. Focus first on just the first row. So these are just heat maps of PSNR, where on the y-axis, I'm plotting model size that's increasing from top to bottom. And on the x-axis at the bottom, you can see signal bandwidth. So this is, I think, maybe easy to see with the grid model. Basically, things should get better as model size increases and as signal complexity, signal bandwidth decreases. So the bottom left is like easy, big model trying to fit easy signal. The top right is hard, small model trying to fit complicated signal. Within each of these types of synthetic signals, the top row is just the raw PSNR of the model fitting that signal. The bottom row is taking whatever that PSNR was and subtracting whatever the grid got in that scenario. So on the top here, these are just a bunch of sort of classic INRs for a feature network, siren, wavelet representation, GA planes we just talked about, instant GP, Gaussian splatting, bake-in. And then the baseline here is just a simple grid with interpolation. So this was like the simplest baseline we could think of. In these second rows, anywhere that's red means this model did better than the grid. Anything that's blue means the grid was better. So one thing that we notice is that I want to point out on the band limited signal, nobody beats the grid. But on these fractal and circle signals, GA planes and incident GP can beat the grid, and sometimes Fourier feature networks. So we're sort of hypothesizing here that Well, firstly, it's clear that which model you should use depends on what signal you have. And that, actually, let me keep going. Okay, so that was all just overfitting. We also tested this on inverse problems, so CT, denoising, super resolution in 2D and 3D. The bottom, I'm just showing what the signals look like. And again, in the top row, I'm showing raw PSNR. In the bottom row, I'm showing difference relative to the grid. So negative means the grid was better. So in CT, grid is always better. Denoising, grid is always better. Really only for this Stanford Dragon are we finding INRs that can actually compress better than a grid. So this is a bit of a maybe surprising negative result. Okay, I think this is just a cool visualization. This is another synthetic signal we came up with. It's just a star target with a bunch of these radial wedges. So you have really high frequencies in the middle and relatively lower frequencies on the outside. I'm just taking all of these models and again fitting it to this signal. I think this figure is hard to read, so I'm going to show this one. This is the error map. So firstly, I just want to talk about the grid. So the grid is very predictable, right? When it's compressed, it's got lower resolution. It's going to have lots of errors at the edges and lots of errors in the middle where the frequency is high. As you increase the resolution of the grid, this center region of high error gets smaller, as you would expect. And eventually, once you have enough parameters, it does a perfect job. What I think is cool about all of the implicit representations is that most of them actually have similar behavior in the sense that when they're compressed, they generally do worse on high frequencies. And as you give them more parameters, that region in the middle where they do poorly tends to shrink. So this gives us maybe a path forward towards trying to measure bandwidth of these different models and figure out which models are best suited to which signals. Okay, so I'll give my sort of hypothesis on this is that, at least from the signals we tested, it seems like GA planes and some of these other implicit representations can offer good compression when the signal has some underlying lower dimensional structure. So if you're trying to fit, say, the surface of an object, that's a 2D function that's embedded in 3D, implicit representations can do well at that and can beat the grid because the grid has to waste a bunch of parameters in this empty space. But if you have a more general signal that's actually volumetric, like a general band limited signal or a natural image or a CT scan, in all these cases, we weren't able to find an INR that actually was compressive relative to a grid. Maybe this is because the signal is actually distributed all the way through the space. And so at least for a band limited signal, maybe it's not too surprising that the grid would be the best. Okay. I think I will stop here. The link up here is to the archive for G-planes. I don't have the link yet for the second part here. This is going to be out tonight. The GitHub's actually already up. The archive will come out tonight. But if you search the name, it'll come up tomorrow. Okay, thank you.
And take some questions as I swap up the.
How do we have the controls back?
Thanks, Sarah. This is cool work. I was wondering if the notion of bandwidth really makes sense. If this bandwidth is really like a global concept, right? And rate basis functions are defining a global frequency. INRs seem to have like frequencies that could be varying. Right?
Yeah, so this is totally true. This is part of why we looked at different signals that have spatially varying local bandwidth. So I don't want to claim that we have like a final answer to what is the bandwidth of an INR, but I getting there by designing signals that you can locally investigate. Yeah, a more fine-grained notion of bandwidth.
Hi everyone, my name is Sunil, and I'm really happy to share my work on hyperspectral neural radiance fields for phenotyping in agriculture. So for some context,
I was doing the annotating thing again.
Yeah. So for some context, what do I mean by hyperspectral imaging. So your traditional images, which are usually, your RGB images, which usually consist of 3 channels, which comprise of information in the visual range of wavelengths from 400 to 750 nanometers usually, which are accumulated over 3 blocks or 3 channels. However, a hyperspectral image, in contrast, each pixel location, it comprises of a spectral curve, essentially. So, for example, if you look at the pink spot at the hyperspectral image, you'll see the corresponding spectral curve at that point. And here's how these pixels change as basically as your the nanometers of the wavelength of the light being emitted or increases. So each specific point comprises of a spectral curve, essentially a continuous spectral curve. Now, there are 2 types of prominent types of hyperspectral cameras. One is your hyper snapshot scanner. The other one is a push broom or a line scanner. Now, your line scanner is the one that's usually used in like most of your applications. Like it's usually mounted on top of a UAV. And so for some context, a line scanner, basically what it does is it scans only a line, and it captures the hyperspectral cube at that specific line in a very specific dimension. For example, in this case, let's call it the X dimension instead of across both spatial dimensions. So since the translation motion usually happens along the other axis, it captures the whole image by basically accumulating information across the perpendicular axis. However, a snapshot scanner in a singular exposure, it captures the entire 2D spatial scene, essentially. So yeah, but both of these scanners come with its own pros and cons. The snapshot scanner, while it captures the full cube with a singular exposure, and yeah, obviously it has a wider field of view, it suffers from low spectral fidelity. This is because snapshot scanners, usually to compromise for speed, what they do is they have a narrowband filter. So they basically disperse the light into multiple wavelengths across the 2D spatial scene. And each specific location only sees a subset of these wavelengths. And then they use some sort of interpolation or demosaicing process to get the whole hyperspectral profile. Now, whereas your push broom scanners, they have higher spectral resolution and they are much less noisy. However, they require either the camera to move across the perpendicular axis or the scene to move. So, and it has a narrower field of view. Now, why do we care about this stuff, right? So usually what we used to do was phenotype. So phenotyping is a process to obtain certain plant-related information like nutrient information, biomass information, or disease prediction. So usually what happens is that you cut off these leaves. You usually you have to dry them, you have to send them to a lab, and then you get these information. However, hyperspectral phenotyping, you can use this spectral information to basically localize the presence of certain undesirable or desirable characteristics like nutrients or diseases, etc. However, the problem is that usually a lot of these methods, they only use a single image to predict the presence of certain characteristics. So single image phenotyping is angle and lighting dependent, and we only get one aggregate measurement per image. So as you can obviously see, if a specific area is much more illuminated, then it dominates more of the features that are extracted. At the same time, angle dependency, so occlusion. So if a leaf is present below, is being covered by another object that's on top of it, so you basically lose a lot of information, which is why can 3D aggregation solve it? So I'm going to skip the 3D previous approaches because they are basically only getting sparse point cloud information instead of a dense 3D reconstruction. So our data set comprises of information over 2 prominent types of cameras, which are the push broom scanner, which is the surface optics camera, and the base spec golden eye camera. And we also collected information, the dense 3D information over 8 scenes, 8 agricultural scenes. So these are all plants that were captured across multiple poses by our snapshot sensor. Similarly, these are the plants that were imaged by our push broom sensor. Now, these were captured over multiple scenes and capturing multiple camera viewpoints and poses. So we have a dense 3D data set now to basically facilitate hyperspectral novel view synthesis. The data set pre-processing, yeah, this is, I'm gonna skip to save for some time. So our method, the main improvement that we make or the main change that we make over your traditional neural radiance field was to model wavelength as radiance and radiance and volume density of each wavelength as a function of that wavelength. So basically what happens is the wavelength is being passed into the network and we get wavelength specific features, which we are then using to predict the radiance and the volume density of that specific wavelength, light at that very specific wavelength. Now, yeah, so we achieve significant gains on noisy base spec scenes. However, on the surface optics scenes, we are still competitive. It's not completely, we're not really losing any information. However, on the snapshot sensors, which are known to be noisy due to their image acquisition process, we actually see a huge improvement over 6 decibels in certain scenes like the Anna Campseros scene. So this is an example of a pseudo RGB render that we produced. So obviously you can see that the color and the rendering is much more accurate in our method compared to previous methods. And yeah, some ablations. We tried out a bunch of different neural architecture schemes. To save some time, I'm not gonna go into much detail, but to sum it all up, our default model, it stays competitive, but there's not really a huge improvement when we actually model it as a wavelength, the wavelength proposal network. The main, I guess, improvement is that we are actually able to reconstruct entire spectral profiles with just incomplete hyperspectral cubes. So when we just train it on every second wavelength or every eighth wavelength, we're still able to get very, very accurate 3D hyperspectral renderings. And yeah, some more examples. So for a summary, we captured, we have two hyperspectral, we have our first ever multi-scene hyperspectral data set, and we have our own lambda conditioned or wavelength conditioned nerve for hyperspectral imaging to encourage consistent spectral rendering. And yeah, that's all. Thank you.